Hello there and welcome to the Sleepymentary channel. Tonight we open the great cosmic library, a place with no shelves, no walls, nowhere only light, dust and time. Every star within it holds a story, and every planet is a page written in the language of gravity. Together they form the architecture of possibility, a grand design that stretches across the dark like music written on silence. Our own solar system is just one chapter in that infinite book, familiar, comforting, almost provincial in its simplicity. But beyond the pale blue halo of home lies an unimaginable diversity twin sun systems that never know true night rogue planets, adrift in darkness, worlds of diamond and vapor metal and storm, each one proof that nature is not content with repetition. It experiments, it improvises, it dreams. So before we continue, hit like and subscribe so you don't miss a single revelation as this story unfolds moment by moment in real time. Tell me in the comments where you're watching, from what time it is there, and whether you believe we're hearing the whole truth about what's unfolding above our heads. And if you want to keep the signal alive, share this video on X, Facebook, Reddit, or even just with the people who still look up at night. You are the reason we can keep following the impossible, and for that, thank you. As you listen, imagine drifting through this cosmic library as a quiet observer moving past the spines of stars that have burned for billions of years. Some of them cradle families of worlds, each different from the next, a living atlas of what gravity can sculpt from dust. Between them, voids wider than imagination, silent isles where galaxies whisper their histories through faint radiation. For centuries we believed the solar system was a closed story, one star, a handful of planets, a perfect order. Then, at the close of the 20th century, the telescope lens sharpened, and the story exploded outward. The first exoplanets appeared, strange, enormous worlds skimming the faces of their stars' gas giants, where years lasted only days. Soon after came smaller, subtler signals, the flicker of starlight dimming as an Earth-sized body crossed in front. And suddenly the night sky changed meaning. Every star became a possibility. Every dot of light was not just a sun, but perhaps a system, a home, a chemistry, a climate, a chance. We now know that planets are not rare accidents. They are the natural consequence of star birth. When a star forms, it does not do so alone. The leftover gas and dust flatten into a disk, a glowing whirlpool of raw material. Inside it, dust clings to dust, pebble to pebble, until small worlds emerge, then collide, merge, and evolve. What begins as chaos resolves into order, and what looks like order always hides the memory of chaos. Gravity is both the author and the editor of this story, patient and relentless. Each solar system then is a memory, a record of motion frozen into shape. The distances between planets, the tilt of their orbits, even their atmospheres are paragraphs written by collisions, migrations, and quiet compromises. Some are harmonious and stable, others are wild, their planets looping on eccentric paths that tell of past violence. Together they remind us that the universe builds not like an engineer but like an artist, sketching, erasing, reimagining endlessly. In this journey we will drift from system to system, from the ordinary to the extraordinary. We will visit places where sunsets come in pairs, where mountains rain molten iron, where seas have no shores, and where worlds float freely between the stars, carrying their nights with them. These are not dreams, they are real. Astronomers have seen their shadows cross the faces of distant suns, measured their atmospheres in the faint fingerprints of starlight, and listened to the gravitational murmurs of unseen giants. What emerges from all these discoveries is something both humbling and profound, the realization that creation itself has no single blueprint. The universe seems determined to try everything. Some stars gather families of giants, others raise only a few small children of rock and ice. Some systems are so tightly packed that 5 or 6 planets could fit comfortably inside Mercury's orbit. Others spread their worlds across distances so vast that light takes hours, even days, to travel from one to the next. In this diversity lies the secret of endurance. Balance is not sameness, it is adaptability. And adaptability is the rule of existence. Whether carved by gravity or by evolution, the cosmos survives by inventing new forms. Worlds bloom and fade, collide and begin again. They teach us that permanence is an illusion, and beauty often hides in instability. As we move through these stories, think of each solar system not as a collection of numbers, but as a living rhythm and orchestra of matter tuned by time. Each orbit, Each resonance, each gravitational tug is a note in a song that began before we were born and will continue long after we're gone. We are simply listening from within one of its quieter movements. If you could float beyond our system and look back, you would see it glowing softly, a faint halo of planets circling a golden heart. Around that heart, everything that has ever lived or thought has unfolded. Yet from a distance, it is one of billions indistinguishable from the next. That is the paradox of existence, singular to us, ordinary to the cosmos. So tonight, as the hum of the world fades and the room grows still, allow your imagination to drift outward past the clouds, past the magnetosphere, past the last whisper of our sun's light, until you find yourself among countless stars, each one a library of worlds. Let curiosity be your compass and wonder your guide. The journey ahead will carry us through fire and ice harmony and destruction, youth and age. It will remind us that planets are not static decorations around stars, they are evolving expressions of possibility, each born from the same laws, yet unfolding in infinite variety. This is the Cosmic Library, and tonight we begin to read its first pages, the stories of worlds beyond our own, the quiet miracles that fill the dark with meaning. Breathe deeply and let your mind drift among the shelves of starlight. The universe has been waiting to tell its story. Imagine standing on a world where the day never looks the same twice. The light shifts from gold to crimson, from silver to violet as two suns weave across the heavens. When one star rises, the other might already be setting, and there are moments fleeting breathtaking when both hang in the same sky, one large and amber, the other pale and distant, painting the land in twin shadows that move in opposite directions. This is the reality of circumbinary planets' worlds that orbit not one but two stars. For centuries, such systems existed only in myth and fiction, Tatooine skies, imagined horizons of double dawn. Yet in 2011, NASA's Kepler telescope confirmed what storytellers had always dreamed, a planet truly circling two suns, balanced in their gravitational dance. It was called Kepler 16b, a world of gas and twilight where every day was a symphony of changing light. At first glance, this seems impossible. How can a planet find peace between two burning giants, each pulling in its own direction? Wouldn't gravity tear such a world apart or fling it into the dark? The answer, surprisingly, is no, because nature, when given time, finds rhythm even in chaos. A circumbinary system is a cosmic partnership, two stars orbiting a shared center of gravity known as the barycenter. If a planet circles both from a distance, its path becomes an elegant braid of motion, looping and curving in ways that seem unstable, yet remain perfectly predictable. As long as the planet stays far enough out, typically 2 or 3 times the distance between the stars, their combined gravity acts as a single steady pull. The chaos resolves into harmony. It is a lesson written in starlight stability as not the absence of motion, but the balance of it. The Kepler mission, watching over 150,000 stars for tiny flickers of shadow, found several of these twin star worlds, Kepler 34b, Kepler 35b, Kepler 47c, and more. Each one challenged our assumptions about where planets can exist. Some circle sun-like pairs, others drift around cooler red dwarfs. In all cases, the pattern repeats order, emerging from dance orbits braided like strands of light. On such a planet, time itself would be layered. The length of a year depends on the orbit around both suns, while the rhythm of day and night shifts as the stars move in relation to each other. Sometimes there might be 2 sunsets a day, followed by hours of dim orange twilight. Other times, weeks, when one sun dominates while the other vanishes behind the horizon. Seasons would not follow simple patterns, they would flow like tides of brightness and shadow, as the geometry of light continually changes. If there were oceans on such a world, their tides would pulse in complicated rhythms drawn by 2 sources of gravity. Waves might rise not in pairs but in chords, sometimes amplifying, sometimes cancelling each other, in the eternal conversation between stars. And if life ever took root there, its biology would learn that constancy is an illusion. Plants might evolve pigments tuned to multiple wavelengths. Nocturnal creatures might move in cycles of alternating warmth. The skies would never settle into repetition, and perhaps neither would thought. Kepler's data also showed something unexpected. These double star systems are not rare. Roughly half the stars in our galaxy are part of binary or multiple systems, which means the phenomenon of 2 suns in one sky could be one of the galaxy's most common experiences. The universe, it seems, loves pairs not just in gravity but in structure, symmetry and resonance. Even the mathematics of these systems tells a story of coexistence. When scientists model them, they find fractal patterns hidden in the equation's pockets of stability surrounded by seas of chaos. Move a planet slightly closer, and the orbit falls apart. Nudge it outward, and it locks into perfect cadence. It's a reminder that harmony is not accidental. It's the product of delicate proportion. Astronomer Jack Lissauer once described these orbits as ballets of balance, and the phrase feels right. In the dark vacuum of space where nothing hears and nothing feels, gravity still composes choreography. Two stars swirl and a planet traces their steps, endlessly adapting to their rhythm. What we call physics might also be poetry, written in the curve of motion and the persistence of order. Think of what it would be like to stand there on a plateau of dark stone watching two suns dip toward opposite horizons. The first sets in gold, turning the clouds into rivers of fire. The second lingers in lavender light, soft and cool, until night comes, not as darkness, but as gentle dimming the sky, deepening into blue. Shadows cross in strange directions. Mountains glow from both sides. And as you breathe, you realize that even here, amid forces that could unmake worlds, something has found balance. That is the quiet miracle of circumbinary systems. They remind us that the universe does not fear complexity. It welcomes it. Where chaos might seem inevitable, time and gravity negotiate peace, and in that peace planets are born. As our journey continues, we'll see that not all systems are so harmonious. Some spin backward, some orbit with defiance as though trying to rewrite their past. But for now, let's stay a moment beneath these twin suns and listen to the light of two hearts beating in one sky. Not every world spins in agreement with its star. Some rebel turning backward, tilted or even upside down, tracing orbits that seem to mock the gentle order of their birth. These are the retrograde worlds, the misaligned wanderers that tell stories of ancient violence written into the geometry of their motion. If most planets are dancers moving gracefully around their sun in the same direction, then retrograde worlds are those who turn against the rhythm. Instead of following the spin of their star, they orbit the other way as if time itself has been reversed for them. Their years unfold opposite to their days, their seasons twisted by the conflict between spin and revolution. On such a world, the sun might rise in the west and set in the east. Winds could flow in inverted patterns and magnetic fields might twist like ropes of light, endlessly fighting for balance. How does a planet end up this way? The universe, though it looks serene from afar, is full of turbulence and collision. In a young solar system, gravity is not gentle. Planets grow from chaos, from a disk of gas and dust, where everything pushes and pulls. A single close encounter can change destiny. A passing star, a giant neighbour, or even a collision between worlds can twist the plane of an orbit by degrees, or flip it entirely. Astronomers have traced some of these events through the Rossiter-McLaughlin effect, watching starlight bend as planets transit across their stars. What they see are the fingerprints of cosmic accidents, planets tilted 30, 60, even 180 degrees from the star's spin. In a few extreme cases, worlds like WASP-17b orbit their suns backward against the current of creation. They are survivors of gravitational combat, living relics of instability that has long since quieted but not been forgotten. Imagine the moment that changed such a world's fate, a youthful solar system crowded with newborn planets, each seeking its path. One giant moves too close, its gravity sweeping across the disk like a storm. The smaller world is caught, spun, and hurled into a new trajectory, no longer aligned but still bound. Eons pass, dust settles. The chaos fades, yet the planet continues its defiant march, circling the star the wrong way forever. Its orbit becomes a scar, a frozen memory of that ancient upheaval. Retrograde motion can also arise when a star's disk itself was skewed from birth. Magnetic turbulence, asymmetry in the collapsing cloud, or the gravitational tug of a nearby companion star can tilt the entire system before planets ever form. In those cases, every orbit may be misaligned, like a set of tilted rings around a crooked axis, not chaotic, just different, carrying the signature of the cloud that birthed them. For scientists, these strange configurations are time capsules. They let us reconstruct the family histories of stars, the quarrels, the collisions, the long gravitational feuds that shaped their systems. By measuring each planet's tilt and orientation, astronomers can replay the past in slow motion, uncovering the violence hidden beneath apparent serenity. And there's something poetic in that, because in a universe governed by order, disorder becomes the record of memory. The scars of chaos are not imperfections, they are evidence of survival. A retrograde world is a living contradiction orbiting in defiance of its star's spin, yet obeying the same laws that govern everything else. It reminds us that harmony does not require symmetry, and that even the most elegant cosmic music includes dissonant notes. Gravity, after all, is both composer and archivist. It writes every disturbance into its score and never erases the lines. If you could look down upon one of these systems, perhaps from far above its star, you'd see one planet tracing its path clockwise, while all the rest flow counterclockwise. It would look almost deliberate, like an accent mark in a sentence, a reminder that perfection is never universal. The universe's beauty lies not in uniformity, but in variation, in the persistence of the strange. For any life that might evolve on such a world, this reversal would shape everything. The sky would move in unfamiliar ways, seasons would drift unpredictably, and the interplay of day and year would twist the rhythm of biology. Even timekeeping itself, the simple pattern of dawn and dusk, would defy expectation. Yet if life arose, it would adapt, and soon the backward would simply become the normal. Nature never argues with circumstance, it learns to live within it. In studying these wayward worlds, we're really studying the memory of motion, how the universe remembers every encounter, every near miss, every brush with chaos. Retrograde planets are not mistakes. They are history made visible. And so when we watch their backward paths through starlight, we're not witnessing defiance, but endurance proof that even in the vast clockwork of the cosmos, not every gear must turn the same way for the machine to keep time. Somewhere out there, a sun sets in reverse. Its planet spins the wrong way through twilight, tracing an orbit that tells of ancient collisions and quiet resilience. It moves not with the crowd, but against it, carrying the memory of its creation like a scar that gleams in starlight. There was a time not long ago when we believed the Earth was rare, a singular oasis adrift in an endless dark. But then we began to listen more carefully to the light of other stars, and the silence gave way to a quiet revelation. We are not alone in the category of worlds. According to the data gathered by NASA's Kepler mission, roughly 1 in 5 sun-like stars may host a planet close in size and temperature to our own. 1 in 5, a modest fraction, yet when multiplied across the hundreds of billions of stars in the Milky Way, it suggests tens of billions of potential Earths. Oceans we cannot see, mountains no eye will ever climb, skies painted by unfamiliar suns. It means that the night sky, that calm dome of glitter we take for granted, is not empty at all. It is an ocean filled with hidden shores. Kepler was launched in 2009 with a simple but profound goal: to watch a single patch of sky and measure the faint dimming of stars as planets crossed their faces. For nearly a decade, it recorded more than 530,000 stars, detecting the flickers of over 2,600 confirmed planets, and thousands more candidates. From those flickers patterns emerged statistics that transformed imagination into evidence. The successor mission, TESS, the Transiting Exoplanet Survey satellite, expanded that search to nearly the entire sky, scanning bright nearby stars. Together they have revealed that planets are not rare outcomes of cosmic chance, they are the rule. Every second star you see tonight likely holds its own small system of worlds arranged in configurations stranger and more diverse than anything we could have dreamed before. Among them are rocky planets like ours orbiting within the narrow temperate band astronomers call the habitable zone, the region where liquid water might exist on the surface. It is a cautious phrase, a scientific restraint might, but even that word holds gravity. The conditions that sustain life here, warmth, atmosphere, chemistry, time may not be miracles but inevitabilities. When a star forms, planets almost always follow, and when planets form, some will fall into that delicate range of distance, where ice melts and carbon breathes. The odds are no longer hopeless, they are hopeful. Astronomers now speak less of if, and more of how many. How many of those worlds keep their atmospheres intact? How many oceans lie beneath clouds we cannot yet pierce? How many sunsets occur at this very moment under skies no one has yet seen? With the James Webb Space Telescope, we are beginning to move from counting to listening, reading the faint fingerprints of molecules in alien air. When a planet transits its star, a fraction of starlight filters through its atmosphere, imprinting a chemical signature. Methane, oxygen, ozone, each line in the spectrum a potential whisper of biology. These are called biosignatures, and they are the closest thing we have to hearing life breathe across the void. Already Webb and its instruments have glimpsed carbon dioxide on WASP-39b methane on distant gas giants, and the promise of water vapour in the spectra of smaller rocky worlds. We are learning to detect not just presence, but personality, the moods of planets written in the colours of their light. Yet the deeper revelation is not in the numbers, but in the silence that follows them. If Earth is not unique, then neither is its fragility. Every world may be common, but every atmosphere is temporary. Every oasis is precious because time is always eroding its edges. Perhaps the universe does not scatter life randomly, but gives it countless chances to begin patient, persistent, and indifferent. Somewhere evolution may already have composed other symphonies of biology, forests of unfamiliar pigments, oceans that breathe ammonia instead of oxygen, eyes adapted to twin suns or dim embers. Or perhaps we are the only verse in an otherwise silent song. Both possibilities are equally humbling. When you stand beneath the stars tonight, consider what that means: that the small blue circle beneath your feet is part of a vast statistical certainty. That even if you travelled for 1,000 lifetimes, you might find another Earth not identical but familiar enough to make you weep. The quiet abundance of worlds tells us something profound about existence. It tells us that life is not written on a single page but scattered across a library of possibilities. It invites us to see the night not as an emptiness above, but as a map of futures, some already extinguished, others still forming. In every faint dot of starlight lies a potential coastline, a river, a field of storms. Some worlds are too close to their suns, their oceans turn to steam. Others too far, their atmospheres frozen into silence. But between those extremes again and again, the laws of physics conspire to create balance. The cosmos, it seems, keeps rewriting the same story with new characters, hydrogen and carbon meeting in countless combinations, always seeking a form that can feel warmth, absorb light, and remember. And so, as you listen to the night, know this: the dark above you is not a void. It is an ocean of light folded into distance, each shimmer a shore unseen, each world a question waiting for someone to ask it. Somewhere a dawn may be rising over a quiet sea 200 light years away. The air might be thick with the scent of unknown rain, the clouds tinted green beneath a red sun. No one is there to see it, yet it happens all the same. Because abundance does not need witnesses to be real. It only needs the patience of the universe and the curiosity of those who look up and listen. Between the stars there are wanderers, worlds without a home. They drift through the galactic dark, carrying no sunrise, no orbit, no sky to call their own. To us they are invisible until chance reveals them like shadows crossing shadows. Astronomers call them rogue planets, but the word rogue feels almost too human, as though they chose to leave. In truth, they were exiled, torn from the systems that once birthed them, set adrift in silence that has no end, and yet they endure. A rogue planet begins like any other. Born from the swirling disk of dust and gas around a newborn star, it grows amid collisions and heat, feeding on fragments of stone and ice. But then comes the instability, the gravitational argument between giants. In young systems, planets tug and wrestle for dominance. One wrong encounter, one brush too close to a heavier neighbour, and the smaller world is hurled outward, gaining speed, till even its star's gravity cannot call it back. Cast loose, it drifts into the cold gulf between suns, a night that never ends, a journey that may last longer than the galaxy itself. Some travel alone, others may roam in silent clusters, remnants of broken systems wandering together like debris of creation. To imagine their surface is to imagine a world of paradox, frozen yet warm inside. Even without sunlight, a planet can keep its heart alive. Radioactive decay in its core, uranium, thorium, potassium, continues to release heat, the same slow fire that keeps Earth's interior molten. If the planet is large enough that internal warmth could sustain subsurface oceans beneath shells of ice like those beneath Europa or Enceladus, pressure keeps water liquid and chemistry persists in the dark, feeding on energy that never sees the light of a star. If life can exist without sunlight here around volcanic vents on Earth's seafloor, then perhaps it could on those wandering worlds as well. Entire biospheres could hide beneath crusts of ice sealed away for billions of years, never knowing the meaning of a dawn. To them, starlight would be a myth, and yet they might thrive. For astronomers, such worlds are ghosts seen not by reflection, but by effect. The only way to find them is through gravitational microlensing. When a rogue planet drifts in front of a distant star, its gravity bends and magnifies the starlight for a brief moment. No light of its own, No orbit to trace, just a flicker, a distortion, a whisper of presence. In that flicker we read an entire story, mass distance and motion. Dozens have been found this way. The Milky Way may hold billions more. Think of that, billions of dark worlds drifting unseen between the constellations. For every star that anchors a system, there may be as many planets adrift, scattered like seeds caught in the galactic wind. The night sky, it seems, hides as much as it reveals. There's something deeply human in their solitude. We look up and imagine motion bound to meaning orbit cycles, repetition. But these worlds know no return. Their years are endless, their paths unrepeatable. They travel not in circles, but in straight lines through eternity. And perhaps that makes them the truest reflection of the cosmos itself. Because the universe at its core is a place of isolation. Stars are born together in clusters, but as they age, they drift apart, pulled by the slow breathing of the galaxy. Every atom, every particle is separated from the next by distance, held together only by invisible forces and fragile memory. Even our own solar system is temporary, its planets destined to scatter one day into the same dark that birthed them. To exist in any form is to be briefly gathered from that emptiness, to shine for a while and then to drift away. Still, the rogue planets remind us that darkness is not death. They are not extinguished, only quiet. Their cores still pulse with hidden warmth. Their gravity still shapes space around them. They remain part of the cosmic web, connected by invisible threads of influence and chance. In the deepest night, they are the heartbeat of persistence, the universe's proof that motion continues even without light. Imagine standing on one of them, wrapped in an endless twilight. The stars overhead do not rise or set. They only drift slowly as you move between them. There is no east, no west, no compass, but memory. And beneath your feet, deep below the frozen crust, an ocean sighs softly in the dark, warmed by the same decay that fuels mountains on Earth. You are utterly alone, and yet the silence is not empty. It is full of continuity, of endurance, of the slow persistence that defines everything the cosmos makes. Perhaps loneliness is not an exception in the universe, but its default state. Stars, planets, atoms, even galaxies, all separated, all drifting, all bound only by invisible forces that reach across the dark. The miracle then is not isolation itself, but that anything ever meets at all. So when we call them lonely travelers, maybe we are really describing ourselves, tiny observers in a corner of one system surrounded by countless unseen worlds, each following its own silent path. And if you close your eyes tonight and let your thoughts drift far enough, you might feel it, that same slow motion, that same pull through the dark. You too are part of the drift, moving through the cosmic night with every star and every wandering world. The universe is not still. It is endlessly in motion, even in its loneliness, even in its sleep. Long before our sun was born, before Earth had oceans or even atoms of gold, other stars had already lived and died. And around some of them, planets still circle ancient survivors from an age when the universe was young, when the first heavy elements had only just begun to appear. These are the fossil worlds, relics of cosmic prehistory, orbiting quietly through the modern galaxy like fragments of the first dreams. To find them, astronomers look for metal-poor stars, a misleading term, because in astronomy metals mean anything heavier than hydrogen or helium. The earliest stars were almost pure hydrogen, born just a few 100 million years after the Big Bang. Only when those titanic suns exploded did heavier elements appear: carbon, oxygen, iron, silicon, the building blocks of rock and life. Each new generation of stars inherited a little more of that cosmic inheritance, enriching the universe grain by grain. So when scientists find a planet orbiting a star almost devoid of metals, they're looking at something extraordinary, a world that formed before the galaxy was mature enough to make many like it. A world built from the barest ingredients, without much iron to give it a core, without much carbon to fill its air, and yet somehow still here. One such relic is Kepler 10b, one of the oldest known rocky planets. Its parent star is about 10.6 billion years old, nearly twice the age of the Sun. That means this planet formed when the Milky Way itself was still assembling, when there were fewer stars, fewer metals, and far more uncertainty. It has circled its star more than 3 billion times since then, surviving impacts, radiation, and cosmic drift, a witness to epochs we can barely imagine. Other ancient systems like PSR B1620-26 tell an even stranger story. It's nicknamed the Methuselah planet, orbiting a binary pair, one, a white dwarf the other, a pulsar in a cluster almost as old as the universe itself. That planet is roughly 12 billion years old, making it more ancient than our Sun's elements. To look at it is to see a survivor from the dawn of planetary formation, a world that has outlived suns. Such planets are poor in metals but rich in endurance. They reveal that planet formation began astonishingly early, not as a late afterthought, but as a natural continuation of star birth itself. Gravity wastes no time. Wherever matter gathers, it experiments. Even in a universe barely out of infancy, worlds were already forming, spinning, freezing, enduring. If you stood on one of those primordial planets, assuming it had a surface to stand upon, you'd see a night sky very different from ours. The Milky Way's spiral arms would not yet have settled. The stars would appear fewer, bluer, younger. The air, if it existed, might carry no oxygen, no ozone, just raw chemistry waiting for complexity. And above you, the light of your own star would be weaker, thinner, its spectrum shifted toward the early colours of creation. Over billions of years, such worlds have survived catastrophes that would erase entire systems near by supernovae, galactic mergers, and the slow reshaping of the Milky Way's spiral arms. Their orbits may have drifted, their skies may have changed beyond recognition, but they remain fossils of formation, holding in their minerals the memory of the first heavy atoms ever made. In their silence lies a truth about time itself. For us, a millennium is long. For a planet, it is a heartbeat. For these ancient worlds, 1 billion years is simply a turn of the page. Their continents, if they have any, have been remade countless times. Their mountains have risen and fallen, their crusts melted and frozen again. Every trace of their youth has been rewritten, except for one, their continued existence. When we study them, we are looking not at the beginning of a story, but at its persistence. They tell us that the cosmos did not need to wait for perfection before beginning. It began with what it had, with sparse materials, with imbalance, with uncertainty, and still it built worlds. In a sense, these planets are our cosmic ancestors. The atoms that form our oceans, our bones, even our thoughts were forged in stars like theirs. Their death scattered the metals that became the next generation of systems, including ours. Every world since has borrowed from their dust. To study them is to trace our lineage back through time to the first places where matter began to hold memory. And there is something profoundly moving in that continuity. It means that even as stars burn out, even as galaxies collide, nothing truly vanishes. The ingredients are passed on. Worlds die, but their matter reincarnates, folded into the next attempt and the next. The universe is not a graveyard, it is a recycling of wonder. So when you look at the night sky and see a faint old star, perhaps yellowed, dimmed by distance, you may be seeing one of those ancient systems still spinning quietly after 10 billion years. Around it, planets continue their patient revolutions, indifferent to our brevity. They are the keepers of cosmic memory, older than every mountain, every ocean, every dream on Earth. To them our world is a newcomer, bright, fragile, temporary. And yet in their endurance, they whisper a kind of reassurance that creation is not a single act, but a continuous process, and that even the oldest worlds are still part of the unfolding. They turn slowly in the dark like ancient stones in a cosmic river, worn smooth by time but never washed away reminders that the universe, though it ages, never truly grows old. In the beginning, every planet is born where it shouldn't stay. The cosmos builds its systems in motion disks of dust and gas spiraling around newborn stars, restless, turbulent, alive. And within those whirling cradles, the worlds we now see as fixed were once travelers slipping through orbits like fish in a current drawn by invisible tides of gravity and gas. We call this process planetary migration, the great reshuffling of infancy. No solar system begins with its planets neatly arranged. Giants wander inward, small worlds are flung outward, and resonances form delicate gravitational rhythms that lock orbits into harmony, like dancers keeping time to a distant drumbeat. Out of this migration, chaos becomes order. Our own solar system bears the scars of such motion. The gas giants, Jupiter, Saturn, Uranus, Neptune, likely began far closer to the Sun than they are today. But as they grew, their immense gravity stirred the surrounding disk. Jupiter, the heavyweight, ploughed through gas and dust like a ship carving a wake. Its movement set off waves that nudged the smaller planets, pulling some inward, shoving others outward. Saturn joined the dance, and together they orchestrated what scientists call the Grand Tack, a migration inward toward the Sun, followed by a sweeping reversal outward again. That journey reshaped everything. Jupiter's inward dive may have scattered early building blocks of planets, starving Mars of material and leaving it small. Its retreat may have saved Earth, clearing a safe corridor for our world to form. Even the asteroid belt between Mars and Jupiter might be a fossil of that migration leftover debris caught between two tides that never settled. And this story isn't unique. Across the galaxy, telescopes have revealed thousands of hot Jupiters, massive gas giants, orbiting their stars in just a few days so close that their atmospheres boil and stream away into space. These worlds cannot have formed there. The heat is too intense, the space too tight. They must have migrated inward from colder regions drawn by friction with the gas disk or by gravitational nudges from other planets. Some stopped just in time. Others kept falling until their stars consumed them entirely. It's a cosmic migration pattern as old as time movement driven by imbalance, corrected by gravity repeated until equilibrium finds a temporary home. In that way, planets are not so different from life itself. On Earth, migration defines survival birds following seasons. Whales chasing warmth seeds carried by wind or tide to new ground. Nothing in nature truly stays where it began. Rivers change course, continents drift, even galaxies migrate through the larger web of space. Motion is not the exception, it is the law. And yet from that ceaseless movement comes structure. When two migrating planets settle into a stable ratio, say one orbit for every two of another, they fall into what astronomers call resonance. It's a gravitational rhythm, a heartbeat of stability amid drift. TRAPPIST-1. A famous system of 7 Earth-sized worlds is a perfect example. Each planet's orbit is locked in harmony, with the next a cosmic choir singing in mathematical precision. Theirs is a migration story that ended not in chaos but in music. Migration then is not destruction, it is choreography. The universe experiments by moving its pieces until harmony appears, and once that balance is achieved it can last for billions of years. But even stability is only temporary. Over eons, as stars lose mass and radiation changes, the orbits drift again. Some planets spiral inward, others are cast out entirely. The cosmos never stops editing itself. Every solar system is a work in progress. Perhaps that is why the universe feels alive, because nothing in it ever rests. Even the most stable orbits are slow dances in a long evolution of motion. If we could watch a solar system form in real time, we would see it as a migration of migrations. Newborn planets carving lanes in gas, sweeping past one another, exchanging momentum in delicate encounters that decide their fates. Some worlds would vanish into the void, others would merge in fiery collisions, and a few, the lucky few, would find calm circular paths around their star, their wandering finally at peace. But peace in cosmic terms is just another kind of motion slowed down. And so when we look at our night sky, at the planets following their patient routes across our heavens, we are seeing the end of one migration, not the absence of it. Jupiter still tugs at us subtly. Earth's orbit still shifts with the slow heartbeat of gravitational tides. Even now, after billions of years, the journey continues too gradual for our lifetimes to notice. Migration is how the universe learns to build. It shifts, tests, balances, and begins again. Every world carries the memory of its motion, the trace of where it came from, the story of what it avoided, and the scars of what it passed through. And in that way, planets are like living beings, each one shaped by the roads it took, defined not by where it started, but by where it finally found balance. So tonight, as you drift towards sleep, imagine those worlds still moving, silent travelers shifting slowly through cosmic seas, following the same eternal rule that guides rivers, winds, and life itself. Nothing in the universe stays where it was born. Everything moves until it learns to belong. If you could stand above a compact planetary system looking down on its clockwork motion, from far above the plane of its orbits, you would see not a peaceful solar order like ours, but a celestial symphony wound tight. Worlds spinning so near their star that a full year lasts only a handful of days. Orbits nested one inside another, each planet chasing the next in perfect rhythm, their conjunctions unfolding like the ticking of a cosmic metronome. These are the crowded heavens, multi-planet systems so compact, so delicately balanced, that all their worlds could fit comfortably inside the orbit of Mercury. To the eye of a physicist, they are masterpieces of efficiency. To the imagination, they are the universe, proving that beauty and density can coexist without chaos. One of the most remarkable examples is TRAPPIST-1, a faint ultra-cool dwarf star only 40 light-years away. Around it circle 7 Earth-sized planets, each locked in gravitational harmony with the next. Their orbits are so closely spaced that from one planet's sky, the neighbouring worlds would appear larger than our moon, gleaming crescents racing across the horizon, each one a visible reminder of the system's perfect order. In TRAPPIST-1, every pair of planets keeps time in resonance, a repeating ratio of orbits like beats in a musical score 8-5, 5-3, 3-2. No collisions, no drift, only an unending dance gravity's own choreography written in silence. The mathematics of such systems is astonishingly precise. Each planet's motion tugs on the next tiny adjustments that prevent disaster and maintain balance. If one orbit shifts, its neighbours respond, distributing tension through the chain until equilibrium returns. The entire structure behaves like a living mechanism, flexible yet stable, as if the universe designed it for elegance rather than survival. Our Sun's family, by contrast, feels spacious and leisurely, but around these dim, cool stars the architecture is compressed. Where Earth takes 365 days to circle the Sun, the innermost planets of TRAPPIST-1 complete their years in just a day and a half, the outermost a mere 19 days. Their proximity creates warmth where little starlight exists. Their harmony protects them from collapse. Nature wastes nothing, it builds densely, efficiently, beautifully. And TRAPPIST-1 is not alone. Systems like Kepler-11, Kepler-80 and TOI-178 show the same astonishing precision chains of worlds orbiting within a fraction of the space between Earth and Venus, all moving in rhythm. Each of these systems challenges our intuition. How can so many worlds coexist in such confinement without disaster? The answer once again is resonance, a gravitational conversation that never stops. In these systems, conjunctions, moments when 2 or more planets align, occur frequently, sometimes every few days. From the surface of one of these worlds, the neighbouring planets would wax and wane in the sky, with predictable grace appearing as luminous disks that cast faint shadows across alien oceans. Their combined gravity might raise tides not just in seas, but in the very crust, subtly shaping geology with every encounter. If life ever arose on one of those worlds, it would grow under skies filled with companions, a night never entirely empty, a constant reminder that it was part of something larger. There would be no illusion of cosmic solitude. The heavens themselves would be busy, full alive. For scientists, these compact systems reveal how efficiently the universe can organize itself. When the protoplanetary disk is thin and uniform, planets grow evenly spaced and settle into synchronized orbits like beads sliding into balance along a string. There is no waste, no wide separation, only precision born of patience. In their architecture lies a kind of humility, proof that the universe can achieve order without vast distances or violent dominance. Harmony does not require emptiness. It thrives in crowding, in negotiation, in the quiet collaboration of gravitational forces. If you close your eyes, you can almost hear it, the rhythm of invisible worlds circling a dim red star, each pulling gently on the next, each trusting the balance that holds them all together. Their motion is steady, ancient, self-correcting, a music not made of sound, but of repetition. Perhaps there is a lesson in that. In nature, perfection often hides in compression, in the spaces where everything must coexist, where compromise becomes stability. Whether in ecosystem, atoms, or planetary systems, the same principle whispers, life and order emerge not from isolation, but from interaction. The crowded heavens are not chaotic. They are deliberate. A silent harmony written into the machinery of space and time, showing us that even in the smallest orbits, the universe knows how to make room for wonder. Not every solar system is built upon stone. Some are made almost entirely of air and ice, grand ghostly families without solid ground, where the only landscapes are clouds, pressure and light. These are the gas-dominated systems worlds that never hardened into rock, where chemistry replaces geography and weather becomes the terrain. In such places there are no mountains, no continents, no rivers to carve. A traveller could fall forever through vapour past endless veils of clouds, tinted by unfamiliar chemistry, violet ammonia storm streaks of methane blue rain made of liquid iron or diamond. These are not metaphors. On some of these planets, the pressure and temperature are so extreme that carbon truly crystallizes into diamonds as it falls. These worlds tell us that composition, the balance of elements present at birth, defines destiny. Our solar system is rich in heavy elements like iron, silicon and magnesium, the essential ingredients of rock. But in some star systems, those elements are scarce. Their planets form mostly from hydrogen, helium, water, and volatile gases, abundant materials that can't easily solidify. The result, a system without firm surfaces where planets remain bloated and ethereal, their cores hidden beneath hundreds of kilometers of atmosphere. One of the most fascinating examples is GJ 1214b, a world discovered by the Kepler and Spitzer telescopes. It's a so-called mini-Neptune larger than Earth, smaller than Uranus, and likely wrapped in a deep steamy envelope of water vapor and hydrogen. If it has a surface, it lies far below crushing pressure, buried beneath layers of supercritical fluids that blur the line between liquid and gas. To imagine standing there is impossible, to exist there unthinkable. And yet such worlds may be among the most common in the galaxy. Astronomers have begun calling them water worlds or sub-Neptunes, but in truth they are more like chemical worlds, laboratories where molecules dance under alien conditions. Their skies are not empty, they are alive with reactions. Ultraviolet light from their stars breaks apart methane, ammonia, and water, creating exotic hazes that turn their atmospheres milky or crimson. The patterns of those colours are fingerprints, spectral clues that tell us how the chemistry of life might differ where rock is absent. Then there are the superpuffs, planets so low in density that they seem to defy logic, vast spheres of gas lighter than cotton. Worlds like Kepler 51b or Hathi P67b have the mass of a few Earths, but volumes nearly as large as Jupiter's. Their atmospheres are swollen by heat, and youth inflated like cosmic balloons. Seen from afar, they are fragile giants, not the hard-walled worlds of stone we know, but delicate envelopes of sky adrift in space. In such systems, the idea of habitability must be rewritten. Life as we understand it, anchored to ground, nourished by oceans, shaped by geology, might not fit here, but perhaps other chemistries do. In the upper layers of these gaseous worlds, temperatures and pressures may briefly mimic those of Earth's lower atmosphere. There, in the thin equilibrium between radiation and gravity, simple molecules could form and linger, droplets, dust, or microscopic colonies of chemistry sustained by sunlight and turbulence. Some scientists even speculate that aerial life could exist in such environments, not crawling across continents, but drifting, feeding on light and convection like plankton in a planetary sky. Even in our own solar system, Jupiter and Saturn hint at this possibility. Beneath their pastel bands lies immense diversity zones of ammonia storms, lightning that crackles through hydrogen seas, and deeper still transitions from gas to metallic liquid, where electrons flow freely, generating magnetic fields that reach millions of kilometers into space. Each layer is a different world stacked invisibly upon the last. These gas-rich planets remind us that the concept of a world does not require solidness. A planet can be a pattern of motion, a chemistry in balance, a self-sustaining system of wind and gravity. To define life's potential only by rock and soil is to underestimate imagination, not ours, but the universe's. And yet there is something melancholy about these families without rock. They are places where no foot will ever touch ground, no river will ever carve memory into stone. Their stories are written in vapor, temporarily erased and rewritten by each new storm. Their surfaces are illusions, shifting boundaries between sky and deeper sky. But they are also places of purity, elemental, primal, close to the way the universe itself began. Hydrogen and helium, the simplest of atoms, swirling, as they once did in the first moments after the Big Bang. In their clouds we see the echo of our cosmic childhood, before rock, before metal, before complexity condensed into form. So when we look at these worlds through telescopes studying the faint dips in starlight as they pass before their suns, we are peering into the earliest architecture of creation planets that never finished becoming solid, still halfway between gas and world. Perhaps one day we'll understand them not as barren but as beautiful, a reminder that not every kind of stability needs a surface, and not every kind of life must walk upon ground. The universe in its generosity builds every possible variation of home, even the ones made only of sky. The universe, when it wishes to be quiet, speaks in rhythm. And nowhere is that rhythm clearer than in the slow, precise choreography of planets bound by resonance worlds, whose orbits are not random, but woven together in harmonic ratios like notes in a cosmic melody. This is clockwork gravity, the quiet music of motion. It is what happens when planets learn to move not as individuals, but as a system, each orbit tuning itself to the next, each revolution echoing the others in time. If you could hear it, it would sound like balance itself. In celestial mechanics, a resonance occurs when two or more planets complete their orbits in whole number ratios. One world circles its star twice for every 3 turns of another, or 3 for every 5 or 5 for every 8. Gravity locks them into rhythm, preventing collision and preserving harmony. Each planet's pull slightly accelerates or slows, the next keeping them all in a repeating pattern that can last for billions of years. Imagine a set of invisible gears turning in space. The cogs are worlds, the teeth are gravity. Their motion is perpetual, not because of perfection, but because of mutual correction. Each planet guards the others from chaos by surrendering a little of its freedom to the group. The system endures through cooperation. One of the most elegant examples is Kepler 223, a system of 4 planets orbiting a sun-like star about 5,000 light-years away. Their orbits form a resonant chain. For every 3 turns of the innermost planet, the next completes 4, the next 6, the outermost 8. Each revolution tugs on the next like a heartbeat, maintaining the rhythm through gravitational feedback. If one world drifts, the others gently pull it back into step. It is a clock made not of metal but of motion. When astronomers modelled its stability, they found that these 4 planets have been in the same configuration for billions of years, a living relic of their formation preserved through pure mathematics and patience. Even more poetic is the TRAPPIST-1 system, whose 7 Earth-sized planets form one of the longest resonant chains ever observed. Their orbits are locked in a pattern so intricate that the timing of each world's transit predicts the next like bars of sheet music. In that star's dim red glow, 7 worlds move together as if guided by an unseen conductor, each keeping perfect time in a composition that never ends. It is easy to forget that resonance is not guaranteed. The early universe is a place of collisions and rearrangements, of migration and loss. Most systems do not achieve such balance. But when they do, when gravity finds that narrow window between chaos and collapse, something almost musical emerges. The equations of orbital resonance resemble the mathematics of rhythm ratios, intervals, beats per measure. Johannes Kepler himself in the 17th century believed that the planets sang not literally but numerically. In his Harmonices Mundi, or Harmony of the Worlds, he compared the spacing of planetary orbits to the intervals of a musical scale. He imagined a celestial polyphony, each planet a voice in a silent chorus. 4 centuries later, modern astronomy has proven him both wrong and right. The planets do not make sound, but they do keep time. Their motions generate measurable frequencies, their conjunctions repeat with the precision of a metronome. If we could translate their orbital rhythms into audible tones, systems like Kepler 223 and TRAPPIST-1 would sing chords of astonishing regularity, their harmonics pulsing across the void like a heartbeat of order amid infinite silence. What makes these systems so compelling is their fragility. One small change, a passing star, a drift in mass, a faint atmospheric loss could unravel the entire pattern. And yet they persist, surviving for billions of years. That endurance is not luck. It is the nature of resonance itself. In a resonant chain, imbalance becomes self-correcting. Disturbance feeds stability. Chaos paradoxically produces peace. Perhaps that is the quiet lesson of clockwork. Gravity harmony is not the absence of tension, but its resolution. The pull that might destroy instead sustains. The struggle for equilibrium becomes the equilibrium itself. Even our solar system carries faint echoes of this music. Jupiter's moons, Io Europa and Ganymede, are locked in a 1-2-4 resonance. Their orbits synchronize so precisely that the same alignments repeat every few days. Those periodic tugs stretch and squeeze Io's crust, heating it until volcanoes erupt like geysers of molten rock. It is a reminder that even harmony can be passionate and even order can create fire. When you look up at the night sky, you see apparent stillness. But behind that stillness lies rhythm and invisible pulse, a cosmic waltz of attraction and release. Every planet, every moon, every ringed world moves in answer to gravity's metronome. The next time you listen to music, imagine the stars tapping along. For the universe is full of instruments and gravity plays them all, not in noise but in timing and pattern, in the quiet perfection of repetition. This is clockwork gravity, the slow patient symphony that holds the heavens together, note by note, orbit by orbit, until time itself becomes a song. The universe, though born from chaos, seems to crave pattern. Even amid turbulence and chance, it shapes worlds that echo one another, siblings of nearly equal size spaced in gentle order, orbiting their star like pearls on a string. Astronomers call this the peas in a pod pattern systems, where planets are strikingly similar, their radii masses and spacing so consistent they seem deliberately arranged. At first, this discovery felt improbable. We grew up thinking our solar system was typical small rocky worlds near the sun, giant gas planets, farther out an uneven family where every sibling has its own temperament. But as Kepler and Tess gathered data from thousands of distant stars, a quieter truth emerged. Our system is the exception. Most planetary families are not so chaotic. Many are symmetrical, balanced, almost minimalist, a kind of cosmic efficiency that repeats the same template again and again. Imagine a planetary system built with a craftsman's restraint. The star forms from a collapsing cloud of dust. The leftover gas flattens into a disk. In that disk, material collects evenly like ripples forming around a dropped stone. Each ring gathers mass in proportion to its distance, and each becomes a planet not very different from its neighbours. The result, a family of worlds that share nearly the same size and composition, each one tuned to the same scale. One of the clearest examples is Kepler-32, a red dwarf system about 1,000 light-years away. All 5 of its planets are roughly Earth-sized and closely spaced, orbiting within a distance smaller than Mercury's path around the Sun. Another, Kepler-80, contains 6 worlds of similar radius, each separated by nearly equal gaps. Systems like these suggest that the physics of planet formation often seeks symmetry not as art but as equilibrium. Why might this matter? Because symmetry fosters stability. When planets are similar in mass, none dominates the others. Their gravitational pulls balance rather than disrupt. Their orbits settle into near-circular shapes, resonant and predictable. Each world's motion reinforces the others like instruments sharing a tempo. It's as though nature prefers cooperation to hierarchy. Astronomers studying these patterns notice that planets in such systems often follow a subtle progression. Slightly larger ones, farther out, slightly smaller ones, closer in a rhythmic gradient, not a random scatter. The spacing ratios between orbits are also surprisingly uniform, usually around 1.5 to 2 times the previous distance. It's as if gravity itself has a sense of proportion, spacing the worlds in accordance with an invisible design principle that keeps the whole structure steady. This idea that order begets endurance echoes throughout physics. From atomic shells to spiral galaxies, stability often arises when things repeat. Electrons find equilibrium in discrete layers, stars in galaxies settle into patterned arms, and planets, it seems, often prefer equal company. To visualize it, imagine looking at one of these systems from above 6 or 7 planets, circling a small star, each separated by the same soft gap, each orbiting with perfect timing. If you drew their paths, they would form nested rings, like ripples in water, unbroken, unchanging. From afar, it would look almost artificial, a symmetry so elegant that if an artist painted it, you might assume the hand of design. And yet it's only gravity unthinking, patient, relentless, shaping chaos into harmony. Even their diversity where it exists follows pattern. In many of these peas-in-a-pod systems, every planet's density is similar too. That means they likely share the same internal structure, rocky cores, thin atmospheres, or water-rich layers. The same recipe repeated under slightly different conditions. In that sense, they are not just neighbours but variations on a theme. It's tempting to wonder whether such systems might also nurture life. If one world lies within the habitable zone, its siblings nearby could share similar climates, similar chemistry. Imagine a star surrounded by half a dozen near twins of Earth, each with oceans, clouds, and seasons, a neighbourhood of possible Edens, each visible from the other's skies. In such a place, the night would not be empty. One could look up and see other blue marbles shining not as distant dreams, but as reachable destinations. Symmetry then may be more than aesthetic. It may be fertile. Stable systems last long enough for atmospheres to form, for chemistry to evolve, for possibility to linger. Disorder can create, but order allows things to stay. And yet beneath all this structure, there's still humility. Even perfect symmetry is temporary. Over billions of years, slight drifts in gravity or stellar brightness can shift orbits, break ratios, rewrite the harmony. The cosmos builds balance, knowing it will one day dissolve it again. The art is not permanence, but grace in impermanence. When we see those peas in a pod through the faint dips in starlight, Each planet crossing its star in rhythm, we are witnessing nature's attempt at efficiency, elegance and peace. It is the universe's quiet reminder that beauty is not a rare accident but a recurring instinct written into its laws. Among the crowded and chaotic architectures of creation, these symmetrical systems shine as examples of cosmic restraint, proof that the same gravity that scatters can also sculpt that even in randomness there lies the possibility of rhythm. In the end, perhaps the universe is not striving for perfection at all, only for balance. And in those balanced families of equal worlds orbiting in serenity around their single glowing sun, we glimpse something profoundly human, the comfort of order, the peace of repetition, and the harmony that makes existence feel whole. There are worlds so close to their stars that night itself cannot exist, where dawn never ends and everything burns. These are the planets of fire ultra-hot worlds that orbit their suns in mere hours, their surfaces heated beyond the melting point of metal, their skies glowing like open furnaces. They are not habitable. They are not merciful. Yet in their beauty there is truth, the kind of beauty that exists only when matter is pushed to its limit. Imagine standing, if one could stand, on a world like Kelt 9b, orbiting a blue-white star hotter than any in our solar neighbourhood. The planet lies so near that its atmosphere is blasted to 4,000 Alaska C, hot enough to vaporize iron and titanium. Daylight there is not yellow, nor even white, it is electric. The air itself radiates light shimmering with metallic ions, turning the whole sky into a molten mirror. There is no ground, only a sea of gas roiling under gravity's grip, where clouds are made not of water, but of vaporized iron that condenses into iron rain as it moves into cooler twilight. Each droplet falls like liquid metal, glinting for a moment, before re-evaporating in the wind, a storm that never ends where weather and chemistry are one. Further out in systems like WASP 76b, astronomers have detected this eerie phenomenon. Directly iron atoms torn from the hot day side drift into the cooler night, condense into droplets, and fall as rain and metallic monsoon under alien stars. The planet's night is still far hotter than any fire on Earth, but the difference between sides is enough to forge weather out of physics. Here even glass becomes part of the climate. On HD 1897433b, winds howl at over 8,000 km/h, H supersonic tempests, carrying silicate dust high into the atmosphere. Those particles melt cool and crystallize as they travel, creating clouds of glass shards that glitter, blue when seen in starlight. If you could watch from orbit, you'd see the planet's azure hue, not from oceans, but from scattering light off airborne glass. Beauty here is violent. Every sense, if they could exist, would be overwhelmed. The heat would erase texture, the air would shimmer with metallic light, the horizon would blur a continuous mirage. Each gust would tear molecules apart, and yet from that destruction emerges colour. The blues of silicate clouds, the orange of sodium haze, the faint green of vaporized copper. These worlds are close orbiting giants, hot Jupiters and ultra-hot Neptunes, victims of their proximity. They were born farther out, then migrated inward, trapped in an embrace with their stars that they can never escape. Their atmospheres are slowly stripped away by radiation tails of glowing gas streaming behind them like cometary banners. In time, many will lose everything, leaving only scorched cores, dead embers of planets, drifting cinders where giants once were. And yet, in the brief span of their existence, they display some of the most complex weather in the universe. Astronomers study them not for habitability but for understanding, because in their extremes, the chemistry of atmospheres is revealed with clarity. Molecules there cannot hide, they split, recombine and glow, leaving spectral fingerprints that teach us how light and matter converse. From Earth, telescopes detect these patterns, the faint dimming as the planet crosses its star, the delicate change in colour that betrays metallic vapour. It's like reading the pulse of a furnace from across the void. In those spectra, scientists have found traces of iron, magnesium, calcium, titanium, oxide sodium, and even vanadium elements usually locked in rock, now freed into flame. The poetry of these worlds lies in their contradiction. They are hostile but radiant. Each is a crucible where elements born in stars return to their fiery origin, a loop of cosmic recycling happening in real time. Matter melts, evaporates, escapes, and perhaps one day will cool again elsewhere, forming new worlds more temperate, more kind. When we call them planets, we use the same word as for Earth, yet their meaning stretches the imagination. They are not spheres of stone, but dynamic laboratories where physics writes its most dramatic prose. Each sunrise is a chemical reaction, each storm a thermodynamic experiment, and though we cannot visit, we can still learn from their endurance. Even here, under endless flame, gravity and motion find balance. The same equations that guide Earth's orbit also hold steady these infernos. The cosmos does not play favourites. Its laws are impartial, elegant and unflinching. If there is beauty on such worlds, it is the beauty of purity of matter stripped bare of energy unrestrained. The kind of beauty that burns to exist. So as you drift into sleep, imagine them iron rain falling through orange clouds, molten horizons wrapped around glowing stars, winds faster than sound whispering through glass dust. A place where day and night are made of fire and still the mathematics of motion keeps the world from breaking apart. Because even at the edge of destruction, the universe insists on grace. Some worlds have nothing left to protect them. Their skies are gone, their oceans boiled away, their mountains exposed beneath a light too fierce to soften anything. They are bare rocks in the light, airless planet stripped to their cores, left to face their stars with nothing but silence for an atmosphere. They began, perhaps much like ours, with clouds and rivers, minerals reacting with air, a fragile balance between warmth and wind. But over time their suns grew stronger, their magnetic shields weaker, and the slow, invisible storm of charged particles, the stellar wind, began to peel their atmospheres away, atom by atom. On Earth, our magnetic field bends those particles harmlessly toward the poles, painting auroras in the sky. But on worlds without such protection, the wind digs deeper. It lifts the upper atmosphere into space, stripping it bare over millions of years. Pressure drops, oceans evaporate. What remains is silence. An entire planet turned into a fossil of itself. Our own Mercury is one such relic. A scarred half-sphere of iron and dust, its dayside scorched, to 430 Degrees its nightside colder than Antarctica's deepest ice. It has no air to share heat, no sky to scatter light. The sun rises there as a blinding disk more than twice as wide as from Earth, so bright that shadows seem carved into the ground. Each crater holds its darkness for eternity, undisturbed by wind or rain. Even time feels still there because nothing moves that isn't struck by an impact. Yet Mercury is not alone. Across the galaxy, telescopes have found countless airless exoplanets, small rocky worlds, so close to their stars that their surfaces glow with molten metal. Many are lava planets, like 55 Cancri, where dayside temperatures exceed 2000 Hekuwangs, hot enough to vaporize rock into atmosphere, and then recondense it each night into molten rain. The entire world breathes rock instead of air, its geology pulsing with heat in rhythm to its orbit. Others farther from their stars are colder, but equally silent, fractured ancient surfaces, recording eons of bombardment. Without weather, every scar remains. Every crater is a memory. These worlds are geological archives, their silence a record of everything that has happened to them, written not in words but in impact basins and mineral veins. Atmosphere loss is not just a fate, it's a biography. It tells us how a planet's heart and field evolve. To keep an atmosphere, a world must have both mass and magnetism. The first provides gravity strong enough to hold gas. The second provides a magnetic shield to deflect the stellar wind. When either fails, erosion begins. Mars offers the cautionary tale: once wet, once blue, it lost its global magnetic field 4 billion years ago. Solar particles began to claw away its sky, and over ages the rivers dried, the seas turned to dust, and the red silence settled in. What we see now is a ghost of a planet that once breathed. Even the word silence takes on new meaning on these worlds. It is not the absence of sound, it is the presence of stasis. No breeze to whisper through rock, no waves to break, only the faint hiss of micrometeorites landing once every few minutes, tiny punctuation marks in an otherwise unbroken quiet. If you stood there in a pressurized suit visor reflecting the star, the loudest thing you'd hear would be your own heartbeat echoing in your helmet. The rest would be the sound of cosmic stillness, the kind that makes you feel the weight of time, and yet even in their barrenness these planets endure. They are the survivors of radiation, gravity and loss. Their surfaces may be stripped, but beneath them lie clues, traces of magnetic minerals frozen, when the core last cooled hints of ancient atmospheres trapped in rock pores, whispers of what once was. To study them is to read history written in basalt and dust. Somewhere billions of kilometers away, a telescope records a faint dip in a star's light, the passing of such a bare rock invisible yet precise. From that single shadow we can measure its size, its orbit, its temperature, even its albedo. And though we will never stand there, we can imagine a scorched world turning slowly an unblinking mirror to its sun. These are the planets that remind us of impermanence, of how fragile air can be, how easily warmth becomes exposure. They show that habitability is not a permanent state, but a moment balanced between gravity's pull and a star's generosity. And they offer something quieter too, the humility of endurance. Even without air they remain, even without colour they reflect. Even stripped of life they tell stories of magnetism, of time, of the raw persistence of matter itself. Perhaps silence is the planet's final language, a way of speaking without sound, of remembering without words. Under the blinding light of their stars, these bare worlds shine, not because they are alive, but because they once were. And in their stillness they whisper to us not of what was lost, but of what endures when everything else is gone. Some worlds are born in the cold and die in the fire. They begin their lives far from their stars, quiet, distant giants wrapped in frost and hydrogen, orbiting where sunlight is faint and time moves slowly. But then something happens, a gravitational disturbance, a tug, a resonance, a nudge from a sibling planet, and slowly over millions of years they begin to fall inward. These are the long voyages, the worlds that migrate across entire solar systems, travelling from frozen outskirts to infernal proximity, becoming what we call hot Jupiters. They are wanderers that traded peace for brightness. Born beyond the snowline where ice and gas are abundant, they grew huge and heavy, their gravity shaping the fates of smaller worlds nearby. But instability, the subtle friction of gas, the influence of a companion star, or the chaos of early planetary motion set them adrift. They drifted inward, pulled by the slow whisper of gravity, and dragged their orbits shrinking year by year until they found themselves so close to their suns that a year lasted mere days, and equilibrium meant survival. In the 1990s, when the first exoplanet was discovered around a sun-like star 51 Pegasi b, it shattered every assumption we had. A gas giant half the mass of Jupiter orbiting its star every 4 Earth days. No one had imagined such a configuration could exist. Planets like that shouldn't be there, yet they were. Now we know they are common. Hot Jupiters exist around roughly 1% of sun-like stars, and they tell a story not of anomaly but of transformation. As they move inward, they carry with them the memory of chaos, a fossil record of the galaxy's early violence. Migration is not gentle, it disrupts everything. Small rocky worlds are flung out or swallowed whole. Moons are stripped disks of debris shredded. The migrating giant becomes both architect and destroyer, sculpting what remains into new harmony. In some systems, this process ends in catastrophe. The planet spirals too close and tidal forces rip it apart, spreading its remains into a ring of gas. Others find balance just before destruction, locked forever in a precarious embrace, orbiting faster than a whisper, hotter than a forge. On many hot Jupiters, the same side always faces the star, a phenomenon known as tidal locking. Their days never end, their nights never begin. One hemisphere is a sea of eternal fire, the other a dark, frozen wasteland. Between them, a narrow twilight band glows in perpetual storm, a river of wind rushing at thousands of kilometers per hour, carrying heat from day to night in a ceaseless looping jet stream. If we could descend into one of those skies, the experience would be surreal. The horizon would shimmer with metallic clouds, iron and silicate vapor glowing orange under starlight. The star would hang fixed overhead, blinding and enormous, while the rest of the universe hid behind daylight that never fades. Below, the planet's atmosphere would twist in supersonic gyres, and deep inside tides, from the star would churn its core like a heartbeat, generating heat from friction alone. This tidal strain, that endless gravitational pull and stretch, slowly decays the orbit. The energy of motion turns to heat, and over billions of years the planet creeps even closer to its star. Some may eventually cross the point of no return, where gravity tears them apart, scattering their substance back into the system that once birthed them. In that way, the long voyage ends where it began, as gas dust and memory. Astronomers have begun detecting these final stages. In systems like WASP-12b, the planet is already being consumed, its atmosphere drawn into a bright ring around the star, glowing faintly with the light of disintegration. Observations show its orbit shrinking measurably, with time a slow spiral inward, a death written in decimals of seconds per year. But if destruction is the final act, the story itself is creation. These voyages teach us how planetary systems evolve, how early chaos gives birth to order. Their existence explains why inner systems may lack small rocky planets. They were swept away by migrating giants. They reveal how gravity sculpts balance through struggle, how every world's position is the product of ancient motion. The journey of a hot Jupiter is a story of extremes from frozen infancy to furnace adulthood, but it also mirrors the universal truth of change. Nothing in the cosmos remains where it began. Stars drift through the galaxy, galaxies drift through the void. Even light bound by nothing is slowed by time and gravity, and yet amid that motion, there is continuity. The same elements that once formed those distant giants, hydrogen, helium, carbon, will one day cool again, reform, reassemble. The long voyage is not a fall, but a cycle, a migration through forms, through temperatures, through states of being. If the universe has a story, it is one of constant rearrangement. The long voyages are its most dramatic chapters, the giants that dared to move too close, and in doing so revealed how systems learn balance through loss. So when you look at a star and imagine its planets, remember, some may have come from far away bearing the memory of frozen dawns. Some may still be moving inward, now invisible but unstoppable. Each one is a traveler, reshaping its sky, rewriting its destiny. In the end, they remind us that distance is never permanent, that everything, even a world, is just passing through. Every story in the cosmos ends the same way in transformation. Even stars, those radiant anchors of stability, are only temporary harmonies between gravity and fire. They spend their lives fusing light elements into heavier ones, resisting collapse through the pressure of their own heat. But when the fuel runs out, when gravity finally wins the argument, the result is both an ending and a beginning. This is what happens when stars explode. A supernova begins in silence, a pause, a tremor, the collapse of a core once able to bear its own weight. In less than a second, that core falls inward with unimaginable force, compressing to the density of an atomic nucleus. The rebound sends shock waves tearing outward through the star's layers. Temperatures surge to billions of degrees. Every atom is shredded and reforged, then light. For a few fleeting weeks, the dying star outshines entire galaxies. Its brilliance spreads across the dark like a cosmic heartbeat visible from millions of light years away. The explosion rips its planetary system apart. Worlds that once basked in warmth are vaporized in an instant. Their orbits erased, their elements thrown into interstellar space. Moon's dust atmospheres all return to the raw ingredients of creation. To witness such destruction would be to watch time reversed, solid turn to gas form, to chaos, matter unbound. Yet even here in the violence there is purpose, because in those final seconds the star forges the elements that make everything solid, everything alive. Iron, nickel, cobalt, gold, all born in that furious collapse. The calcium in our bones, the silver in our veins, the oxygen in our lungs, all were made in explosions like these billions of years before Earth existed. The debris of a supernova becomes a stellar nursery. The shock wave expands, compressing nearby clouds of hydrogen and dust, triggering the birth of new stars. Each generation inherits the ashes of the last, growing richer in metals and complexity. Out of death comes diversity, out of chaos structure. Every new world is built from fragments of the old. In this way, a supernova is not an end, it is recycling on a galactic scale. A single explosion can seed thousands of future solar systems. Its expanding remnants, filaments of glowing gas and dust stretch across light years, painting the sky in tendrils of color. The Crab Nebula, the Veil Nebula, the Cassiopeia. A remnant all are tombs that became gardens. Within their folds, new molecules condense, new planets form, and new stories begin. Imagine it, a young world, billions of years later, circling a quiet star, its mountains rich in metals, forged in that ancient blast. A child there lifts a golden ring to the sunlight, unaware that the atoms gleaming on her hand once burned inside a star that died before the Milky Way had its spiral arms. That is the symmetry of cosmic life, the inevitability of return. Even in destruction there is generosity. The supernova does not simply end, it gives. It spreads complexity through the universe, ensuring that the next generation of stars will shine with richer chemistry, that their planets will have the raw materials for oceans, atmospheres, and biology. The physics is relentless, but the poetry is undeniable. A collapsing star releases more energy in a single moment than our sun will emit in 10 billion years. The blast sends shockwaves travelling at thousands of kilometers per second, compressing everything they touch. Behind them, the expanding gas cools dust forms, and gravity begins again the slow work of building. Death feeds creation. Destruction becomes design. This is how the universe renews itself, not through mercy, but through process. There are no funerals in space, only transformations. And yet from our small vantage point, the idea carries emotion. We are made of this cycle. We are the descendants of explosions, the dust of once burning hearts scattered across time and gathered again into consciousness. When a star dies, it does not vanish. It changes form, and somehow some of that starlight learns to wonder about itself. Every time we look at the night sky, we're seeing the afterglow of ancient endings light that left dying stars before our species had eyes to see. We're surrounded by reminders that everything beautiful is temporary, and that impermanence is the very engine of creation. The next time a supernova flares in some distant corner of the Milky Way, its shock wave will sweep through interstellar clouds, shaping future suns that will one day rise over new worlds. Perhaps on one of them, life will look up and feel what we feel awe, fragility, belonging. For that is the final truth of these explosions. They are not acts of violence, but of continuity. In the language of physics, they are feedback loops of matter and energy. In the language of awe, they are the heartbeat of eternity. Everything we are, every breath, every thought, every story was once inside a star that could no longer hold itself together. And so when stars explode, they do not end the story. They turn the page. There are worlds so vast, so adorned that their beauty defies proportion, planets circled not by thin, elegant halos like Saturn's, but by rings so immense they could swallow a star. These are the colossal ring systems of the cosmos, vast disks of dust, ice, and shattered moons, circling giant planets in slow, luminous silence. To imagine them, we must first imagine scale. Saturn's rings, wide enough to fit 9 Earths side by side, would seem delicate compared to these. Around the star J4517, 420 light-years away in the constellation Centaurus, astronomers found evidence of a planet whose ring system stretches 200 times larger than Saturn's. If you replace Saturn with this world often nicknamed Super Saturn, its rings would dominate Earth's sky, filling it from horizon to horizon, brighter than the moon, an arch of light wrapping the entire heavens. The planet itself, J4517b, may be as massive as a young brown dwarf, a failed star, and its rings may extend tens of millions of kilometers large enough that they would eclipse the host star for weeks during transit. When astronomers first recorded the event, they saw starlight dip not once, but dozens of times as different ring bands passed across it. The pattern was intricate, rhythmic, like a code of shadows written in dust. What could create something so enormous? The leading theories trace their origin to destruction, the slow violence of gravity reshaping matter. A moon wandering too close is torn apart by tidal forces, its rock and ice stretched into a stream of debris that flattens into a disk. Or perhaps the planet captures a passing comet swarm, their orbits colliding and spreading into mist. Over time, collisions grind the fragments smaller and smaller until the ring becomes smooth, a seamless band of reflective dust, each particle obeying the silent geometry of motion. These rings are not static. They are living systems constantly replenished by impacts, constantly eroded by light and magnetism. Their structure reveals the language of gravity gaps, where shepherd moons carve lanes, waves, where resonances ripple through the dust. Around Saturn, those patterns are measured in kilometers. Around J1407b, they stretch across millions. If you could stand on one of J1407b's moons, if any survive, the sight would be beyond comprehension. The planet would fill half the sky, ringed by a layered horizon of silver arcs stretching outward into darkness, each one glowing faintly with starlight reflected from frozen dust. The inner rings would shimmer gold, the outer ones fade to blue, each hue marking a different mineral, a different story of collision and creation. And above it all, the tiny distant star would appear as a candle behind a stained glass window, sometimes hidden, sometimes revealed as the planet's rotation carried the rings between you and the light. Recent models suggest that such systems are transient. They cannot last forever. Within a few million years, the dust will either drift inward, forming moons, or be blown away by stellar radiation. We may be witnessing these giants in their adolescence planets, still surrounded by the debris of their own formation, not yet fully settled into maturity. The rings then are both graveyards and wombs, the remains of shattered moons, and the birthplace of new ones. In their dense lanes, particles collide and clump, growing slowly into larger bodies, the same process that once built planets from dust around stars. What we see in miniature is creation repeating itself again and again at every scale. The discovery of J147b and its like has changed how astronomers think about planetary systems. We once imagined rings as fragile ornaments confined to gas giants and limited in size. Now we know they can be vast, dynamic, and common in youth. Infrared surveys hint at other candidates. Faint dips, irregular eclipses, clues that somewhere unseen. Other worlds are encircled by structures grander than stars themselves. Perhaps in the future, telescopes will resolve them directly. Colossal disks glowing like halos around invisible worlds, their rings casting shadows across interstellar dust. Each one will be a portrait of balanced destruction, becoming beauty, fragmentation, becoming order. Because that is what rings are: architecture born from aftermath. They exist at the threshold between chaos and symmetry, between gravity's violence and its grace. They remind us that even in the wreckage of a world, the universe arranges its ruins into something astonishing. And maybe that's their truest lesson, that nothing once broken is truly lost, not even a moon. The debris simply learns to orbit differently to find harmony in pieces. In the quiet light around J147b, fragments of ice and stone still circle endlessly, tracing their luminous geometry around a planet we can barely see. A ring wider than a star, built from everything that once fell apart, still turning, still shining, still beautiful. Not every world must orbit a star. Some may find their light reflected from another world, a sun in miniature glowing beneath a shared sky. These are the giant moons, companions of massive planets that wander within the habitable zones of their stars. And among them may exist some of the most promising, most poetic possibilities for life in the galaxy. Until recently, moons seemed secondary quiet satellites to the true stage of planets. But as telescopes grew more precise, astronomers began to realize that the opposite might also be true, that moons themselves could be worlds large enough to hold air oceans, even ecosystems. In theory, a massive planet, a gas giant like Jupiter or Saturn, orbiting within its star's temperate zone, could host moons as large as Mars or even Earth. Around such a titan, those moons would bask not only in starlight, but also in the reflected glow of their parent planet, warmed by tides, protected by magnetic fields, and forever part of a double sky. We have not yet confirmed an exomoon with certainty, but signs have begun to emerge. The most intriguing candidate is Kepler 1625b, a possible Neptune-sized moon, orbiting a Jupiter-sized planet about 8,000 light-years away. The data is fragile, a faint dip in brightness, a tiny timing offset, but if true, it suggests that moons can grow far larger than anything in our solar system, and that realization changes everything. Because moons add a new dimension to the habitable zone, the region where temperatures allow liquid water. A moon around a giant planet doesn't rely solely on distance from its star. It can draw heat from tidal, flexing the gentle squeeze of gravity that warms its interior, as happens on Jupiter's moon Europa or Saturn's Enceladus. It can absorb the faint continuous glow from the planet's reflected light. Even the planet's shadow, which would bring brief rhythmic eclipses, might help regulate temperature and climate. Imagine one such moon larger than Earth, with seas pulled into rhythmic tides by the gravity of its planet. In its sky, the planet would dominate everything, an enormous striped orb filling half the horizon, glowing softly even when the star has set. Clouds would catch both lights golden from the sun, copper from the planet's reflection, painting the world in dual shadows. Nights would never be fully dark. The forests might shimmer faintly with bioluminescence. The oceans might mirror two suns at once. If life evolved there, it would live beneath cycles unlike anything on Earth. Days might be measured by the moon's spin, but seasons could be dictated by its planet's orbit. Eclipses would darken the world at predictable intervals, turning noon into twilight. Tides would rise to staggering heights, sculpting continents and climates. To the creatures born in such a rhythm, this duality would be nature's normal, not confusion, but harmony. And the parent planet itself, seen from the surface, would be more than a spectacle. It would shape everything. Its magnetic field could shield the moon from solar wind. Its radiation belts might light the polar skies with permanent auroras. Lightning storms in the planet's atmosphere could flicker like distant weather seen from across an endless horizon. If we could visit, we'd find an ecosystem lit by two kinds of dawn. One direct, one reflected, a choreography of light and motion. Ice caps glowing faintly with planetary shimmer. Nights glowing with blue-green phosphorescence under the planet's gaze. Perhaps even civilizations looking up, seeing not just one source of warmth, but two intertwined in orbit, an eternal reminder that balance is possible even in complexity. Scientifically, such moons might be more stable than many free planets. Their orbits are anchored by their planet's gravity. Their climates can remain moderate thanks to tidal heating and long-term orbital resonance. The push and pull that might seem violent from afar becomes a steady rhythm of renewal tectonics magnetism, seasons all fed by motion. Some models even suggest that there may be more habitable moons than habitable planets in the galaxy. If every giant planet hosts several large satellites, then for every Earth-like world there could be dozens of potential moon worlds quietly circling their own small suns. The galaxy's true abundance of life may be found not in planets, but in their companions. Emotionally, the thought is humbling. We're so used to being the center of our own sky, our sun our only light. But perhaps elsewhere under another firmament, beings stand on a shoreline beneath twin illumination, their star and their planet, and look upward not at isolation, but at belonging. Their myths might speak of reflection and reciprocity. One light born of another one world warmed by two hearts. In that sense, the universe itself becomes a metaphor, gravity binding. What might otherwise drift apart, light, shared between companions, warmth multiplied by relationship. The rise of giant moons reminds us that home need not be solitary. It can orbit something larger, share its light, and still be its own. In their imagined skies, a planet blazing like a nearby god, a star beyond, we glimpse the universe's most elegant balance intimacy on a cosmic scale. Some planets turn alone. No moon keeps them steady. No companion pulls their seas. No second light shares their sky. They spin through their years without reflection. Worlds without companions governed only by their star and the silent mathematics of motion. At first, this might seem unremarkable. Many planets we know, Mercury, Venus, are moonless and they endure. But a closer look reveals a subtler truth. The presence or absence of a moon changes everything. It is the difference between a world that breathes in rhythm and one that drifts between extremes. Earth, for example, is balanced by an invisible conversation. Our moon, born from a colossal impact billions of years ago, is not just decoration, it is an anchor. Its gravity stabilizes Earth's axial tilt, keeping it near 23.5 degrees. That tilt is what gives us seasons, weather cycles, and a relatively gentle climate over geologic time. Without the moon, simulations suggest Earth's axis could wobble chaotically, swinging between 0 and 60 degrees. Ice ages might come and go within centuries. Deserts could freeze while poles melt. The moon also stirs our oceans. Its pull drives tides, mixing waters, regulating coastlines, and perhaps in life's earliest days helping chemistry find rhythm between wet and dry, tide and retreat. Without that constant tug, early life might never have learned the patience of cycles. A world without a moon lacks that discipline. Its seas are quiet, its days too uniform, its nights too still. Over eons, its tilt might wander unpredictably, creating unstable climates. Sudden ice ages, violent monsoons, unpredictable sunlight. For complex life, such instability could be ruinous. On Mars, we see a preview. Its two small moons, Phobos and Deimos, are too tiny to help. Over time, Mars's tilt has swung wildly, sometimes near upright, sometimes leaning so far that its poles face the sun. Each shift rewrote its climate-trading equatorial warmth for polar thaw. Rivers once flowed, then froze. Dunes marched where seas had been. The absence of a strong moon meant the absence of continuity. And yet, there is poetry in their solitude. A moonless world is self-contained. Its nights are pure, unbroken by reflected light. Its horizons remain stark and simple. Such planets turn with a private rhythm, their only partner, the star that feeds them. On their surfaces, the shadows are absolute, the stars sharper, the silence deeper. If you stood on one of them, you might notice how their nights feel infinite, No great satellite rising, no familiar pattern of tides, no gentle light to measure time. Only the faint wind of the atmosphere, the hum of the star beyond, and the knowledge that you are orbiting alone. From a dynamical view, their loneliness has consequences. Without a large moon to distribute angular momentum, the planet's rotation may evolve differently. Some may slow too quickly, their days lengthening until one side scorches and the other freezes. Others may tumble irregularly, their poles wandering like compass needles. Over millions of years, even the rhythm of sunrise and sunset could change. The moon in that sense is a clock, and without it time itself becomes less predictable. Still, not all moonless worlds are unstable. Some find equilibrium through mass and distance alone. Venus, for instance, has no moon yet maintains a consistent tilt, but at a cost. Its rotation slowed, its atmosphere thickened, and it became a furnace. Its calm is that of stagnation, not balance. Its stillness hides an unbreathing sky. Astronomers studying exoplanets now ask, could life thrive on such worlds? Perhaps if other stabilizers exist, multiple neighboring planets, tugging in harmony or magnetic fields strong enough to buffer change. But the odds shrink. For every Earth-like system, there may be countless planets where rotation, climate, and orbit dance without rhythm, never finding the steady beat that life requires. When we look back at our moon bright against the night, we see not only beauty but partnership, a gravitational dialogue that has shaped everything from tides to time itself. Remove it, and Earth would be a stranger, a world of erratic seasons and restless seas where survival might mean constant adaptation. So the next time you see the moon rising pale, silent, effortless, remember that it is more than decoration. It is a guardian of rhythm, a counterweight against chaos. It makes our world spin reliable enough for memory, its tides regular enough for growth, its sky steady enough for hope. And somewhere out there, countless planets orbit without such grace, turning too fast, leaning too far, their oceans unmoved, their nights unlit. They remind us that companionship, even cosmic companionship, is not inevitable. It is a gift. For in the grand mechanics of the universe, balance is never guaranteed, it must be shared. Not every moon is born where it belongs. Some are older than the planets they orbit. Wanderers adopted long after their birth relics of ancient chemistry that preserve the memory of a younger universe. They are the ancestor moons, the cosmic elders, whose orbits tell stories of migration, capture, and the quiet persistence of matter through time. In the great drama of formation, most moons begin as children of their planets, condensed from the same disk of gas and dust, sharing composition, motion, and destiny. But not all followed that script. Some were outsiders passing through, at the right moment slowed just enough by gravity and friction to be caught. In a galaxy where billions of worlds drift in proximity, such cosmic adoption is not rare, and each capture carries with it a history written in atoms. Our own solar system bears their signatures. Look at Triton, the largest moon of Neptune. It moves the wrong way, retrograde orbiting opposite the planet's spin, a sure sign it was captured. Its path is tilted, its motion unnatural, its presence disruptive enough that it likely destroyed any original moons Neptune once had. Yet beneath its icy crust lies something precious, the chemical memory of the Kuiper Belt, that distant realm beyond Neptune, where ancient ices preserve the earliest compounds of the solar nebula. Triton is a refugee from that frontier, a frozen time capsule spiraling around a planet it never knew in youth. Captured moons like Triton are isotopic fossils archives of an earlier era. By studying the ratios of isotopes in their ices and rocks, the specific fingerprints of oxygen, nitrogen, carbon scientists can trace where and when those atoms formed. Different regions of the solar nebula cooled at different rates, leaving distinct isotopic patterns. These are the tools of cosmic forensics, matching chemical signatures to their birthplaces, reconstructing the journeys of worlds across billions of years. The technique has already revealed surprising histories. Mars's tiny moons, Phobos and Deimos, once thought to be captured asteroids, now seem compositionally closer to Mars itself, perhaps remnants of an impact. Yet other irregular moons circling Jupiter and Saturn in eccentric tilted orbits are clearly foreign bodies, fragments of colliding asteroids, comets, or even dismantled dwarf planets. Each one preserves a different epoch of the solar system, pieces of the same grand mosaic scattered and reassembled by gravity. Beyond our system, astronomers believe such adoptions are common. In young planetary systems where gas and debris swirl thickly, temporary captures happen often. A passing planetesimal may fall into orbit around a giant slowed by drag from the surrounding gas. Some stay for a moment, a few thousand years, before escaping again. Others remain forever transformed from wanderers into moons. In those adoptions, the universe reveals its instinct for preservation. Even chaos has compassion. Even collisions can become kinship. If we could walk the surface of an ancestor moon, we'd be standing on prehistory material, older than its parent planet, older perhaps than the star itself. The air, if it had any, would taste of chemistry from the dawn ammonia and methane unaltered since time began. Its rocks would carry isotopic stories of early condensation before heavier elements spread evenly through the nebula. It would be like walking through a museum where the exhibits are still alive, orbiting quietly in the cold. Some theorists even suggest that life's first ingredients might have spread this way, biochemical hitchhikers aboard captured moons. Organic molecules forming in one system could be transported across interstellar space trapped by another planet's gravity, and preserved in its shadow. If so, ancestry in the cosmos is not linear, but adoptive worlds raising children, not their own spreading chemistry like inheritance across the galaxy. To study these moons is to trace lineage backward through the tangled family tree of creation. Each one adds a chapter to the story of how matter travels, how dust from one star's death becomes the crust of another's moon, how ice from the outer reaches ends up orbiting a world warmed by sunlight. The chemistry is the same, only the relationships change. In that sense, ancestor moons remind us of something quietly profound, that origin and belonging are not the same. A world can be born in one place and find purpose in another. Gravity does not ask permission, it invites. It gathers what drifts and through its pull transforms strangers into family. So when we look at Neptune's pale companion, or at the tilted orbits of irregular satellites around Jupiter and Saturn, we are seeing adoption written in motion, lives reshaped by proximity, balance and chance. Each orbit is a story of acceptance. Each isotopic ratio, a whisper of the past saying, I was here before you, but I chose to stay. And as they circle in their quiet arcs, ancient, borrowed, enduring, these ancestor moons remind us that the universe keeps everything, even the lost, in motion. That in the endless gravity of creation, nothing is truly orphaned. There are worlds that should not exist yet do. Planets that orbit not warm suns, but corpses that burned out remnants of stars that long ago destroyed everything around them. And yet, against all odds, they persist, turning faithfully around embers of unimaginable violence. These are the pulsar planets, the first exoplanets ever discovered, and perhaps the most poetic of all life and order reborn around death. In 1992, astronomers Alexander Wolszczan and Dale Frail made a discovery so strange that many doubted it could be real. They were studying a pulsar named PSR B125772, a neutron star 2,300 light-years away, the ultra-dense core left behind after a supernova. It spins hundreds of times per second, emitting radio pulses with clock-like precision. But something they noticed was making those pulses arrive slightly early, then late, then early again, a rhythm within the rhythm. By measuring those variations, they realized the impossible three small planets were tugging gently on the pulsar, altering its timing by milliseconds. Planets circling a corpse. The idea was shocking. A pulsar is the remnant of a collapsed star barely 20 kilometers across, yet containing more mass than the Sun. Its gravity would crush mountains into atoms. Its magnetic field is trillions of times stronger than Earth's, its radiation lethal. How could planets survive that? How could they form after such annihilation? And yet they had. Perhaps they were survivors, fragments of the original solar system that endured the explosion, coalescing again from the debris. Or perhaps they were newborns formed afterward from dust, and heavy elements ejected by the supernova recycled in orbit around the neutron star. Either way, they proved a cosmic truth more profound than any single discovery, that creation does not end when destruction begins. Those first pulsar planets were named Draugr Poltergeist, and Phobetor, mythic titles for worlds circling a ghost. They are small, rocky and dark, receiving no light, but bathed instead in radiation. Yet they orbit in perfect order, as if time itself, shattered by the supernova, had found a new rhythm. A pulsar's light is not gentle. Its beams sweep through space like the blades of a cosmic lighthouse, each rotation sending a pulse that could sterilize any known life. But between those lethal flashes, these planets endure, orbiting through silence, frozen and invisible, the geometry of survival carved into their paths. And perhaps that is what makes them beautiful. For even in death, the universe cannot stop building patterns. Even in ruin, it creates balance. Physically, these systems are marvels of precision. Because pulsars spin with incredible regularity, far more stable than any atomic clock, the smallest disturbance in their timing can reveal orbiting companions. That is why the first exoplanets were found not by light but by time itself. The faint wobble of a dead star told us that planets were not rare miracles, they were inevitable. Today we have found thousands of exoplanets, from hot giants to cold dwarfs. But the pulsar worlds remain a kind of origin myth for our understanding of the cosmos, the proof that planetary formation is resilient. That order can arise from chaos, that a system can rebuild itself, even after apocalypse. Imagine standing on one of those worlds, a surface of carbon dust and iron frost lit only by the pulsing beam of its star. Every few milliseconds the landscape would flash in harsh white light, then vanish again into total blackness. The ground would be silent, the air non-existent, the sky filled with the relic glow of a star that once gave warmth, but now gives only rhythm. And yet even there the laws of physics hold. Gravity still binds. Orbits remain true. Motion continues. In that there is metaphor and mercy. The pulsar planets are reminders that endings are never absolute. When a star dies, it leaves behind not emptiness but potential. Its scattered atoms can assemble again. Its collapsed heart can still keep time. Its debris can find new form. Every atom in our bodies, every molecule that makes breath and thought possible once belonged to a star that died. We too are built on the same principle: life, emerging from remnants, order following catastrophe. The pulsar planets are the cosmic mirror of that truth, showing us that rebirth is not a miracle, it is the universe's default state. So when we speak of life after death, we need not speak metaphorically. It is happening continuously everywhere. The ashes of stars become the dust of worlds. The remnants of explosions become the seeds of stability. Around a dead star in Centaurus, 3 tiny planets still orbit with precision so perfect it rivals any machine we have ever built. Each pulse of that neutron heart marks the persistence of structure, the endurance of pattern, the echo of life. Because the universe, even when it ends, something never stops creating. And in the cold, regular heartbeat of a pulsar, we hear not mourning, but continuation. There are worlds where time itself runs differently, not because of relativity, but because of velocity. Planets that race so close to their stars that a full year lasts only a few hours. Worlds that live and die in the time it takes us to sleep. These are the ultra-short period planets, and they exist at the edge of possibility, where gravity, heat and speed conspire to rewrite the definition of endurance. Imagine a planet circling its star once every 6 hours. Its orbit lies so tight that the entire solar system it inhabits could fit within the diameter of the Sun. From such a world, the host star would fill half the sky, a blazing wall of light and fire. The planet's motion would be so rapid that centrifugal force constantly strains against gravity tides rising not from oceans but from the very crust itself. The laws of motion remain the same, but everything feels faster, louder, more precarious. Many of these planets are rocky remnants, the exposed cores of once larger worlds stripped of gas and mantle. What survives is a sphere of iron and stone enduring heat that can reach 3,000 degrees C. On some metals glow red on the surface. On others, rock evaporates and condenses again in a thin silicate atmosphere. Daylight and destruction are the same thing. The most extreme known is K2.137b, a planet roughly Earth-sized that completes an orbit every 4.3 hours. At that pace, the difference between sunrise and sunset is meaningless. The planet is tidally locked, one hemisphere in perpetual day, the other in eternal night. The day side faces annihilation. The night side freezes in darkness, its mountains crusted with metallic frost. Between them lies a twilight band of continuous storm, a belt of molten clouds and hurricane-force winds, where matter itself circulates from vapor to liquid and back again. On such a world, a year one full orbit passes faster than the span of a human dream. Each orbit brings tidal flexing so violent it melts rock beneath the crust. Each hour-long season reshapes the surface. And yet despite this violence, these planets persist, held together by gravity's last thread. Their tidal friction is immense. The constant stretching and squeezing generates heat from within, slowly stealing orbital energy and causing the planet to spiral ever closer to its star. Over millions of years it will cross the Orosh limit, the boundary where tidal forces exceed self-gravity, and the planet will disintegrate. Its fragments will form a ring, then a dust stream, then nothing. In their last moments, they shine faintly in infrared, their surfaces glowing like embers in a cosmic forge. Astronomers find these worlds by their brevity, the tiny rapid dips in starlight as they transit again and again hundreds of times a week. They are so near their stars that their survival defies simulation. Some may be ex-Mercuries, the metallic hearts left behind when their outer layers boiled away. Others may be failed comets or captured debris briefly stable before succumbing to heat. To stand on one if you could would be to experience the meaning of haste. Your horizon would never darken, your shadow would never move. The ground beneath you would tremble from internal tides. A single orbit a year would pass in the time it takes to eat a meal, and yet the world would never cool, never rest. From afar, though, there is a strange serenity to their repetition. Each orbit perfectly timed, each transit repeating with machine-like regularity. In their self-destruction, they create a rhythm, a heartbeat of fire. To astronomers, these flickers are not chaos, but precision clocks ticking faster than thought, their timing so stable that they help refine our measurements of stellar mass and density. And beneath the data lies something quietly human, a sense that even in extremity the universe keeps time, that even a world orbiting on the edge of disintegration can move with elegance. The fastest years remind us that endurance is not measured in duration but in constancy, in the refusal to lose rhythm even when the end is near. They burn, they orbit, they hold their shape a little longer against the inevitable pull, and as they do, they mark the passage of cosmic time, turning again and again in the shortest of years, teaching us that motion, not permanence, is the truest form of life. There are worlds that know no land, no continent to break the horizon, no mountain to hold the sky, only water, endless and deep. They are called ocean planets, but even that word feels too small. On these worlds, water is not a feature, it is the planet itself. Imagine a globe completely covered by sea, a hydrosphere so vast it stretches from one pole to the other in unbroken continuity. The waves never meet land because there is no land, only layers upon layers of liquid and ice, pressed into strange unfamiliar forms by pressure so immense that water behaves more like metal than fluid. Beneath the upper layers of wind-whipped ocean light fades quickly to darkness. Temperatures rise and pressure multiplies until ice forms not from cold but from compression. These are not the crystalline patterns we know on Earth, but exotic ices, ice fix, ice 7, ice X phases, where molecules are locked together tighter than steel, yet still drifting on slow currents deep within the planet's heart. Between these layers, pockets of liquid water may remain separated by miles of solid ice, a vertical ocean tiered and silent, carrying heat and chemistry downward in slow ancient tides. The most studied candidate is GJ 1214b, orbiting a small red dwarf 40 light-years away. It is about 2.7 times the size of Earth and appears to be neither fully rocky nor fully gaseous, a world of warm water and vapor wrapped in a thick, steamy atmosphere. Temperatures there reach hundreds of degrees Celsius, but the immense pressure may keep its oceans liquid beneath the haze. Observations with the James Webb Space Telescope have revealed a heavy clouded sky rich in water vapor and methane, the first real glimpse of a world that might be an ocean from crust to core. If such a planet could host a life, it would be an existence beyond any terrestrial metaphor. No coastline to define distance, no seasons shaped by land. The sun filtered through permanent clouds would appear as a pale circle smudged by mist. Winds would drive planet-wide storm cyclones that might circle the globe without ever exhausting themselves. Gyres the size of continents, lightning illuminating waves 100 meters tall. In the upper layers, where light still penetrates, chemistry could awaken. Simple carbon molecules stirred by ultraviolet radiation might combine, forming long chains, precursors to biology adrift in a sea without boundaries. Deeper still, where pressure creates stability and warmth seeps upward from the interior, there might exist hydrothermal oases, not on seafloors, but within the ice itself, pockets where heat meets water, a cradle for endurance. If intelligent life evolved there, it would know a world without sky. Its civilizations might rise on floating colonies or drift beneath the surface, guided by bioluminescent maps of current and temperature. Its myths might not speak of land, but of density, the quest for the perfect depth where life and light balance. Its concept of direction would be vertical, not horizontal, shallower, deeper, nearer to heat, nearer to pressure. Scientifically, ocean planets tell us how generous the universe can be with habitability. Water, the simplest solvent, the most common molecule in the cosmos, exists everywhere. Hydrogen and oxygen meet, but too much of it changes everything. A world rich in water may never develop plate tectonics. Its seafloor lies buried beneath kilometers of high-pressure ice. Without volcanic recycling, nutrients might stagnate. Without exposed rock, there is no weathering cycle to balance atmosphere and ocean. Yet life, if it exists, could adapt slow microbial perpetual. The endless ocean becomes both womb and wall. It nurtures and confines, offering stability while erasing distinction. There is no above or below, only gradients of temperature and light chemistry and time. From afar, such planets might appear as dim, bluish spheres, clouds of steam wrapping oceans that never sleep. Their beauty lies in subtlety, the perfection of water's persistence, the quiet endurance of matter that refuses to stay still. In every ripple, pressure transforms. In every layer, physics becomes poetry. These are worlds without beginning or end, only circulation, heat, rising storms, churning molecules, cycling through infinite combinations. If we could drift above one, we'd see a mirror to our own planet, magnified and purified, an Earth, with no boundaries, an ocean that forgot to stop. And perhaps somewhere beneath those eternal clouds in the twilight between heat and depth, something moves, a pulse, a pattern, a thought, born not from land but from liquid memory itself. Because life, it seems, does not need a shore, it only needs somewhere to flow. Among the infinite diversity of worlds, there are some that glimmer in theory like jewels, planets made not of silicate and iron, but of carbon compressed and crystallized under unimaginable pressure. They are the diamond planets' worlds, where geology and gemology become the same thing, where mountains might sparkle and rain could fall as liquid carbon freezing into brilliance before it hits the ground. The idea sounds like fantasy, yet it arises naturally from chemistry. Stars, like people, differ in what they leave behind. When a star and its planets form, their composition reflects the balance of elements in the surrounding nebula. Most systems, including ours, are oxygen-rich, meaning silicon and oxygen bind early, creating rocks and water. But in some regions of the galaxy, particularly around carbon-rich stars, that balance tips the other way. Oxygen becomes scarce, carbon abundant. In such systems, planets condense from carbide dust rather than silicates. Iron still sinks to the core, but above it forms a mantle of graphite, carbide and diamond. Deep inside, where pressures rise to millions of atmospheres, graphite transforms into crystalline carbon. The result, a world that is literally diamond from the inside out, a solid sphere of gemstone locked beneath dark skies. One of the most famous candidates is 55 Cancri, about 40 light-years away. Twice the size of Earth and orbiting its star every 18 hours, it was once thought to be the first confirmed diamond planet. Its extreme heat, more than 2,000 degrees Celsius, suggested that any carbon within might exist as molten diamond in its interior. Later measurements revealed a more complex mix of elements, but the possibility remains carbon worlds could be common wherever stars are born with the right chemistry. Such planets would look nothing like Earth. Their skies might shimmer with hydrocarbon haze, their mountains black and glossy, their rivers, if they exist, thick with tar and methane. Beneath the surface, layers of graphite would give way to dense diamond, a structure so hard it could trap heat for millennia. Lightning in those atmospheres might crystallize soot mid-air, creating microscopic diamonds that fall like snow. To an observer, they would not glitter in the way we imagine. Space has no sunlight to catch a facet, but rather absorb light, dark and radiant at once, beautiful through restraint. The astrophysics of their creation is straightforward. The philosophy it provokes is less so. A diamond on Earth is a symbol of value, permanence, love, a miracle of compression turned into beauty. But in the cosmos, such value becomes meaningless through abundance. A diamond planet could contain quintillions of carats, enough to make the concept of rarity absurd. The universe, it seems, is indifferent to what we cherish. What we call precious is only what is scarce. The cosmos, generous to excess, does not measure worth that way. And yet there is poetry in that indifference. A diamond planet shines not to be admired, but simply because physics demands it. Its hardness, its luster, its endurance, all byproducts of equilibrium. Where pressure and carbon meet, crystal forms. Where time and gravity persist, brilliance becomes inevitable. Imagine standing on such a world if you could. The ground beneath your feet, black and mirror-like, reflecting a dim, distant star. The air thick with hydrocarbons, smelling faintly of tar and metal. The heat so intense that carbon itself flows like honey beneath the crust. You look up and see no water, no clouds, only the shimmer of infrared light, and beneath you, stretching for thousands of kilometers, a mantle of diamond, silent, perfect, eternal. It is a strange inversion of human dreams. Here, entire worlds are made of what we prize most, yet in that abundance the meaning of value dissolves. Beauty, when universal, becomes ordinary. And perhaps that is the truest cosmic lesson, that worth is not written in substance, but in contrast. Earth is rare not because of its materials, but because of its balance, its imperfections, its variety, its mix of elements that allow for change and life. The diamond planets remind us that perfection can be sterile. A flawless crystal is unchanging, eternal, yes, but lifeless. The universe's brilliance lies not in purity, but in diversity, in the tension between fire and froststone and air order and chaos. So when we imagine these shining spheres adrift in the dark, let us not envy them. They are beautiful, but they do not feel the beauty they hold. They are hard, eternal, and utterly still, the opposite of everything that breathes. Perhaps then the greatest diamond in the cosmos is not a planet at all, but a mind that can look into the void and wonder. Not all planets are modest. Some are colossal, swollen, luminous, heavier than anything we imagined. Others are fragile, airy, barely holding themselves together. Together they form what astronomers call the cosmic zoo of giants, a gallery of extremes where the very definition of a planet begins to blur. On one side of the spectrum lie the superjupiters, vast spheres of hydrogen and helium, with masses up to 20 times that of Jupiter. They are not stars yet, they border on becoming one. Add just a little more mass and the pressure at their cores would ignite deuterium fusion, the faint brief burning that defines the lowest rung of stardom. At that threshold, around 13 Jupiters in mass, a planet becomes something else, a brown dwarf, a failed star that glows softly with the heat of its own collapse. These worlds are heavy beyond comprehension. Their gravity is so intense that they compress themselves tighter rather than growing larger. A super-Jupiter twice as massive as Jupiter might be only a few percent bigger in radius. Density becomes destiny. Their cores are packed with metallic hydrogen, a phase where protons and electrons flow freely like molten metal. If you could see them up close, they would gleam not from reflected light, but from their own stored heat, dull red embers fading slowly into blackness. Orbiting near their stars, some of these giants become even more extraordinary. WASP 18b and HAT P Totosuba, for example, are massive enough to warp their stars' shapes and alter their magnetic fields. Their gravitational tides pull entire suns slightly out of round. Their atmospheres are superheated furnaces where molecules break apart and recombine with every sunrise. They are proof that planets can rival stars in power, if not in fire. But move to the opposite end of the scale, and you find their strange fragile opposites, the super-puffs worlds so light that they are less dense than cotton candy. Their discovery shocked astronomers. Planets like Kepler 51b and D have masses only a few times that of Earth, but diameters nearly equal to Jupiter's. Their densities are so low, around 0.3 grams per cubic centimetre, that they could float in a bathtub filled with water. How can something so vast weigh so little? Their atmospheres hold the answer. These are young, bloated planets still warm from formation, their hydrogen envelopes expanded by stellar heat. Their gravity barely restrains them. Ultraviolet light from their stars constantly erodes their outer layers, sending streams of gas into space like vapour from boiling water. They are temporary worlds, planetary soap bubbles destined either to shrink or to vanish entirely, leaving behind small rocky cores. This contrast, the crushed and the hollow, the dense and the delicate, defines the diversity of the cosmos. Between them lies every imaginable variation. Saturn-like giants of ice and ammonia, scorched hot Jupiters that orbit in days, cold wanderers drifting between stars. Some of these giants were born where they now lie. Others are migrants flung inward or outward by gravitational brawls in their youth. The result is a menagerie of contradictions, a reminder that the word planet is less a definition than a spectrum of endurance. In this zoo of extremes, categories begin to fray. Where does a planet end and a star begin? A brown dwarf fuses deuterium briefly, then fades, yet by mass it may equal a giant planet. Some form in disks around stars like true planets. Others form independently, collapsing from clouds like stars. They blur the taxonomy we try to impose, reminding us that the universe doesn't care about our neat boundaries. If you could line them up from superpuff to super-Jupiter to brown dwarf, you'd see the cosmos experimenting with volume and weight, testing the elasticity of matter itself. The densest worlds are compressed to near incompressibility. The lightest are expanded to absurdity. Both obey the same physics, yet their outcomes could not be more different. Even visually, they would be opposites. The massive ones compact, dark, reflective like polished obsidian. The light ones translucent, hazy, veiled in pale gas. One built of gravity's dominance, the other of its mercy. And through them all runs a quiet theme, the relativity of importance. Mass does not mean permanence. Lightness does not mean weakness. Some of the superpuffs will lose their atmospheres and survive as rocky worlds. Some of the super-Jupiters will fall into their stars, ending their grandeur in flame. The universe builds giants not to glorify them, but to explore what's possible between balance and collapse. If you stand beneath a superpuff sky, the horizon would fade into haze. Your world would tremble under a gravity so low you could leap for minutes. If you stood on a super-Jupiter, impossible though it is, the very atoms in your body would be crushed to dust in microseconds. And yet both kinds of worlds belong to the same family, both orbit their stars, both contribute to the same cosmic equilibrium. The cosmic zoo of giants is more than spectacle. It's a meditation on excess and fragility. It shows us that creation does not favor one form of power. It explores them all. Some worlds rise through gravity's grip, others drift through gravity's grace. Between the two, the universe keeps its balance, proving again and again that what matters most is not size or mass or brilliance, but the capacity to endure. Some worlds do not simply reflect light, they become it. They turn their stars into mirrors glowing so brilliantly that their entire faces shimmer like liquid silver. These are the mirror-bright planets, their skies metallic, their clouds made of vaporized minerals, their brilliance so intense that they rival their own suns in radiance. They are worlds that have quite literally captured light. Astronomers measure this luminosity as albedo, the fraction of light a planet reflects. Earth reflects about 30% of the sunlight that reaches it, Jupiter 50. But a few exoplanets approach the impossible 90% or more. They shine like polished gems, their atmospheres woven from microscopic mirrors, droplets of titanium oxide, silicate dust, or aluminum clouds suspended in heat and motion. One of the brightest ever found is Kepler 7b, a giant world orbiting its star so closely that it completes a year in 5 days. Despite that nearness where we'd expect darkness from scorching heat, it gleams with an albedo higher than Venus, the brightest planet in our own sky. The reason lies in its cloud tops, shimmering layers of reflective silicates, tiny glass-like particles that scatter starlight rather than absorb it. Each grain is a floating prism catching and bending the light of the star until the planet itself glows. Still brighter perhaps is LTT 9779b, a hot Neptune with temperatures above 800 C hot enough to vaporize metal. Its atmosphere is laced with molten titanium and aluminum oxides, which condense on the night side into metallic clouds, literal vaporized metal, forming droplets that rain back toward the day side before evaporating again. It is a world of glass storms where silica dust is whipped around the planet at thousands of kilometers per hour, each grain sparkling like diamond dust under relentless starlight. Seen from afar, such a planet would not look solid but fluid its brightness, waxing and waning as cloud belts shift as metallic rain falls and re-evaporates, as winds redistribute brilliance from one hemisphere to the other. Its orbit would trace a halo of glinting reflections like a rotating mirror ball suspended in the black. Imagine orbiting close to one of these worlds. As you approach, the light would grow almost painful reflections so intense that shadows disappear. The planet's day side would appear molten, its curvature defined not by color but by sheen, a continuous flare of silver-gold radiance. The horizon would ripple with metallic clouds, their tops flashing like waves on Mercury seas. Every particle of dust would act as a tiny sun scattering light in all directions until the difference between day and planet vanished. Yet this beauty conceals extremes of violence. Beneath those mirrored skies, temperatures reach thousands of degrees, winds scream faster than sound, the atmosphere is constantly destroyed and remade metals condensing into droplets, then vaporizing again in endless circulation. It is an engine of reflection light turned into weather. The physics is both simple and miraculous. When light strikes these high-altitude metallic clouds, most of it bounces back into space. Because the gases below hydrogen, helium, sodium are nearly transparent, the reflected light dominates the view. The result is a planet that paradoxically looks bright because it fails to absorb. It is a mirror sustained by motion, a portrait of how chaos can masquerade as clarity. Some of these worlds may even reflect their stars so effectively that they cast moving beacons into interstellar space, glimmers detectable light years away, flickering like cosmic lighthouses. As they orbit, the brightness varies a flash at full phase, a dimming at transit, a rhythmic pulse like a heartbeat made of light. In that modulation, astronomers read their composition, their winds, their weather. Philosophically, they pose a quiet question. What does it mean to shine in the universe? These worlds create no light of their own. They only borrow it, scatter it, return it. Yet, they are among the most visible of all planets, luminous through reflection, not creation. Perhaps that is its own kind of beauty. Not the brilliance of self-fire, but of borrowed radiance, a reminder that even the most inert surfaces can become dazzling when light finds them. That reflection, not generation, can make something seen across the void. If you could drift above one of these mirrored worlds, you would feel both awe and distance. The star beneath your feet would shimmer in every direction, refracted through storms of molten glass. The clouds would move like silver smoke. The air itself would gleam. And as you orbited, you'd see your own reflection flicker in the curved horizon, tiny, fleeting, swallowed again by brightness. These are the planets that hold light captive only to release it in infinite directions. They remind us that the universe does not hoard beauty, it scatters it endlessly in fragments of shimmer across the dark. And in every reflection, something larger shines back, not the light of stars, but the act of being seen. Far beyond the warmth of familiar suns, there are worlds that move so slowly their years outlast civilizations. They circle their stars in orbits that take thousands of Earth years to complete, so distant that sunlight arrives as a whisper, a memory rather than a glow. These are the planets of frozen distance where heat is rare, light is thin, and endurance replaces change as the measure of existence. Out here, thermodynamics rewrites itself. At such ranges, starlight provides almost no warmth. Surface temperatures plunge toward the cosmic background hundreds of degrees below zero. Even gases like nitrogen, oxygen, and carbon dioxide freeze into solids. The atmosphere collapses, falling as frost. A planet that once had clouds now has a crust of air layered with ancient snow made from what once was wind. The physics is brutal yet exquisite. Each molecule of gas robbed of energy slows until it bonds to its neighbours, a crystal lattice of frozen weather encasing the planet in silence. And yet not everything freezes. Deep within these worlds, heat persists, the quiet, stubborn warmth of radioactive decay still radiating from the core after billions of years. That remnant energy may keep layers of liquid water locked beneath the ice oceans, hidden under kilometers of frozen shell. We see this principle close to home in the outer moons, Europa Enceladus Titan, but the same applies to planets on the edge of starlight. Beneath their frozen surfaces, tidal or internal heat can sustain vast seas that have never known a sunrise. If life ever arose there, it would live by the rhythm of warmth, not like microbial civilizations powered by chemistry, rather than photons surviving where sunlight has never reached. Astronomers suspect such worlds are common. Some orbit faint red dwarfs whose meager light allows wide, stable orbits. Others are giant planets flung outward by early gravitational battles, wandering in loops so broad that a single year might span the rise and fall of species. To stand upon one would be to see your star as a bright bead in the black, its warmth a memory too distant to feel. The sky would not have blue, only clarity. Shadows would be made not by light, but by the absence of stars behind you. On some frozen atmospheres, rise and fall with the planet's slow motion through its orbit. As it nears its starry sublimates, creating a thin, transient sky, a fleeting season of vapor and wind before freezing out again during the long cold aphelion. A single orbit might include an age of ice, a brief thaw, and another age of ice climate not measured in years but epochs. Even in that deep stillness there is movement. Every few centuries a meteor breaks through the frost, scattering vapor plumes like ghosts. Tectonic stress can fracture the ice, revealing liquid water that refreezes with a soundless crack. The planet breathes, but its breath is measured in millennia. From a distance, such worlds gleam faintly blue-white pearls of reflected light, wandering near the limit of their star's gravity. Beyond them lies only the interstellar dark, the border where planets can drift free and become rogues. These outer sentinels mark the final edge of a system, the last bound orbits before freedom. Their beauty lies in their patience. They are the archivists of time, preserving the chemistry of their youth under ice thicker than mountains. Every atom, every isotope remains almost unchanged since formation. In their frozen stillness, they carry the original signature of their stars like fossils of the early nebula, kept cold enough never to decay. And if we could touch one chip its ice and hold it to light, we would see not emptiness but continuity. The same water that once drifted through the galaxy before finding a home, the same elements that once burned in ancient stars. They are not dead worlds, they are resting ones, waiting perhaps for the next warmth, a passing star, a flare of radiation, or a billion-year slow melt from within to awaken their hidden oceans once again. Because even at the edge of starlight, energy endures, and where energy endures, possibility never fully ends. So when we look into the darkness beyond Neptune, beyond the Kuiper Belt, into the space between stars, we might imagine these slow, cold sentinels still turning each one a monument to the persistence of matter, to the patience of water, to the quiet will of worlds that refuse to vanish. The universe may blaze with stars, but its truest strength is found here in the frozen distance, where even silence keeps orbit. Not every world follows a perfect path. Some tilt until their poles face the sun. Others stretch their orbits into long ellipses that drag them through fire and frost each year. Some spin one way while their orbits lean another, their equators and seasons forever at odds. These are the planets that live between chaos and order, the cosmic improvisations that emerge when gravity forgets to be gentle. In the textbook image of a solar system, orbits are neat and circular, aligned in a flat plane like beads on a disk. But nature seldom obeys geometry for long. Over eons, collision, close encounters, and passing stars bend and twist the dance. A near miss between two giants can tilt one's axis by tens of degrees. A rogue body from another system can stretch orbits into eccentric ovals. Even a slow internal shift, a migration of mass or resonance between moons, can turn a stable rotation into a tumbling spin. Our own solar system bears those scars. Uranus lies almost on its side, its poles taking turns as hemispheres. Its bizarre tilt likely came from a collision with an Earth-sized body early in its history, knocking it into a perpetual roll. Neptune's moon Triton orbits backward, evidence of a violent capture. Mars's chaotic tilt wobbles over millions of years, freezing and thawing its poles in slow planetary breaths. Even Earth's stability, the steady rhythm of its 23.5-degree axis, is a delicate balance, anchored by the moon's gravitational counterweight. When orbits tilt, climates rewrite themselves. A small change in angle alters sunlight's reach, turning continents to tundra or ocean to desert. In extreme cases, a planet might experience hemispheric seasons lasting centuries, one pole scorched for generations, the other locked in night. Eccentric orbits amplify the chaos further. Worlds on elongated paths swing close to their stars, heating to infernal temperatures, then retreat into cold, shadowed space. Their atmospheres expand and contract with each pass, producing global storms of condensation and thaw. For life, such oscillation could mean extinction, or just possibly adaptation beyond imagination. The causes are manifold, yet the principle behind them is simple. Gravity remembers everything. A close encounter leaves a trace in altered trajectory, a shift in inclination that can persist for billions of years. When two stars brush past one another in their galactic drift, they can tug at each other's planetary systems, reshuffling orbits like cards. A planet thrown slightly off axis will never forget. Its seasons will bear the memory forever. In this chaos, though, lies a strange kind of beauty, because misalignment is not the end of order, it is the beginning of new kinds of it. A tilted world still finds rhythm in its motion. Its day lengthens, its year bends, but its gravity holds it together. Some may even become more habitable for its oblique rotation, distributing heat across wider latitudes, eccentric orbits stirring atmospheric dynamics that keep oceans liquid. Chaos paradoxically can preserve balance through motion. Astronomers see this duality written across exoplanet catalogues. Planets like Kepler 413 Zoe, which wobbles dramatically as it orbits two suns, experience wild swings in illumination, a cosmic kaleidoscope of dawns and twilights. Others, such as HD 806b, travel in extreme ellipses that heat them to near melting at perihelion, before freezing them solid weeks later. These worlds are laboratories of instability, yet they endure. Their very existence proves that the universe tolerates asymmetry and even thrives on it. If you could stand on such a planet, you would know time differently. The sun might rise in one place and set in another, then vanish for years. Seasons would have no schedule. The constellations would never repeat exactly. The horizon might glow with auroras born of magnetic chaos, and winds could change direction not by hour but by epoch. It would feel unpredictable and yet on some deeper level steady, because every eccentric world, no matter how misaligned, obeys its star's gravity perfectly. Its irregularities are only the surface ripples of an underlying mathematical harmony. That is the quiet revelation hidden in their motion. Chaos is not the opposite of order, it is its expression through complexity. Every tilt, every wobble, every unpredictable season is the residue of history, the geometry of memory. When we look up and trace their paths, we see not failure but flexibility, proof that even when cosmic structure is disturbed, it does not collapse, it adapts. Orbits shift, climates transform, axes lean, yet the motion continues elegant in its irregularity. Perhaps that is the lesson of the tilted worlds, that balance does not mean stillness and harmony does not mean symmetry. The universe, like life, sustains itself not by resisting change, but by absorbing it, by finding order inside the storm. And somewhere far beyond, under a slanted sky and an uneven sun, another planet turns wobbly, imperfect, radiant, still keeping time with the cosmos that made it. Long after the planets have formed and the great migrations have ceased, something remains: the dust. Thin, cold, persistent. A veil of scattered light and silent collisions drifting between the worlds that survived and the fragments of those that did not. This is the endurance of dust, the faint memory of creation still suspended in orbit. Every solar system begins in dust and everyone ends with it. Out of microscopic grains of rock and ice come the seeds of planet specks, clumping into pebbles, pebbles into stones, stones into worlds. But not all of it finds a home. Much of the primordial matter never joins a planet at all. It lingers orbiting in broad debris disks and asteroid belts, circling the star like the residue of thought after action. Over billions of years, those particles collide and grind against each other. Asteroids shatter, comets crumble, meteoroids vaporize into gas. Each impact creates more fragments, a permanent conversation of destruction and renewal. The result is a faint glowing haze seen in many young star systems, rings of dust backlit by starlight, visible even from hundreds of light years away. In our own solar system, that legacy shines as the zodiacal light, a soft triangular glow, visible from Earth just before dawn or after sunset. It is sunlight scattered by dust particles left behind by ancient comets and colliding asteroids still orbiting in the plane of the ecliptic. To the naked eye, it looks like a pale mist rising from the horizon. To astronomers, it is the fossil breath of planetary birth. Each grain in that light has a story. Some are older than Earth itself, unchanged since the solar nebula. Some are the ashes of recent impacts, fresh fragments chipped from asteroids only centuries ago. Together they form a continuous record of cosmic weather, the slow erosion of structure, the gentle return of matter to its simplest form. In young systems, the dust is thicker, almost architectural. Around stars like Beta Pictoris and Fomalhaut, massive debris disks stretch tens of billions of kilometers wide, bright arcs where collisions are still sculpting new worlds. We can watch these disks change in real time, a cloud forming here, a gap opening there as planets sweep through them, clearing paths like plows in snow. Even destruction becomes a creative act. Each collision adds to the light. Each impact writes new texture into the system's story. Dust paradoxically endures because it is fragile. It resists permanence by refusing to settle. While planets are bound by gravity and fate, dust drifts, pushed by stellar radiation, perturbed by passing bodies, carried outward by the solar wind. Some of it escapes entirely, leaving the system to wander the galaxy, carrying with it the chemical memory of its birth star. And some of that drifting matter eventually returns, falling into other systems, seeding other worlds. In that way, dust is the cosmic messenger carrying elements forged in one sun to become part of another's planets, and perhaps the raw materials of life. When you breathe the oxygen in your lungs and the carbon in your cells were once part of such journeys, grains of dust that survived the fall of stars and the rise of planets. Even today, our solar system is still not finished. Between Mars and Jupiter, the asteroid belt remains a half-formed world, a planetary embryo that never coalesced. It hums with quiet motion, billions of fragments orbiting in balance, colliding just often enough to remind us that creation is ongoing. Elsewhere, the Kuiper belt beyond Neptune whispers of cold beginnings and incomplete endings, frozen dust, ancient ice, and the faint sunlight of distance preserving the early chemistry of the solar system like an untouched archive. In the larger view, dust is not the debris of failure, it is the persistence of memory. It records what the heavy bodies forget. Planets may melt, collide, and be remade, but dust remains to tell the story of what was once solid. Each grain is a chronicle of temperature, radiation, and time, a book written in microscopic layers, legible only to light. If you could hold a single mote of interplanetary dust in your hand, it would be older than any mountain, older than any planet, older perhaps than the sun itself. It would be a fragment of a fragment, yet within it, the architecture of stars and the chemistry of life would coexist, proof that endurance does not require grandeur, only the will to persist in orbit. At night, when the zodiacal light faintly glows over the horizon, a triangle of brightness. Where the sun has just set, we are seeing our own history scattered but unforgotten. The shimmer of everything that ever was still turning, still reflecting, still there. In that faint glow lies the oldest truth of the cosmos, that nothing ever truly disappears. It only becomes dust, and dust remembers. There is no fixed address for life in the universe. Even the so-called habitable zone, that delicate ring where warmth allows liquid water, is not a line etched in space, but a moving frontier. It drifts as stars age, as orbits wobble, as time itself alters the meaning of just right. We often imagine it as static, a golden region, where an Earth-like planet could quietly orbit forever bathed in steady light. But in truth, habitable zones migrate inward or outward with a star's evolution, or multiply in complex systems where more than one sun casts its heat. They are zones in motion, shifting oases on an ever-changing desert of temperature and time. When a star is young and faint, its habitable zone lies close, so close that only worlds hugging their suns could hold liquid water. As the star matures and brightens, that zone moves outward. The inner worlds bake, outer, icy bodies thaw. For our sun, the habitable zone has already crept across space. Billions of years ago, Mars may have stood near its heart rivers running skies thick with vapor. Today it is dry and distant, while Earth remains balanced only for a while longer. In another billion years, our own oceans will boil, and the zone will pass us by, leaving Earth behind as another fossil of lost habitability. But even this slow migration is only part of the story. Around binary stars, the dance becomes more intricate. Two suns moving around a shared center of mass create overlapping regions of warmth and shadow that pulse with rhythm. Planets circling both stars, circumbinary worlds can experience alternating seasons, not of tilt, but of orbit. Two dawns, two twilights, two competing tides of light. The habitable zone itself oscillates, swelling and contracting as the stars move, forming a cosmic heartbeat of potential and peril. There, life would not simply adapt to climate, it would adapt to choreography. Elsewhere, systems with multiple stars create temporary oases, periods of equilibrium lasting thousands, maybe millions of years before instability ends them. A planet might find itself within the gentle warmth of a twin-star embrace. Its oceans liquid, its atmosphere calm until the geometry changes and one star drifts away, pulling the light with it. The world freezes, life collapses, and the zone migrates again. Each flicker of habitability becomes a brief, luminous note in the long symphony of cosmic time. Even in single-star systems, these transitions shape evolution. A dying sun expands into a red giant, pushing the habitable zone outward past its old borders. Icy moons, once locked in cold, awaken for a geological instant, their surfaces melting chemistry, quickening, perhaps even forming life that lasts only for the brief span of their parents' last warmth. Life, if it emerges, there would live in borrowed time, a civilization built in the twilight of its star, knowing the dawn will never come again. From a cosmic perspective, these shifting zones are not exceptions, but the rule. Habitability is dynamic, a moving wave of possibility traveling through systems over eons. It lingers, here, fades there, returns somewhere new. Stars breathe life outward as they age, then draw it back as they fade. If the galaxy were a living organism, its pulse would be measured in these expansions and contractions, the flow of heat and chemistry through billions of temporary Edens. For scientists, this fluidity changes everything. It means we must look not only for planets in the right place now, but also for those that once were or will be. The fossils of lost oceans, the signs of temporary thaw, each may hold lessons about life's adaptability, its tendency to bloom in every window of opportunity, however brief. Philosophically, the idea is humbling. We like to think of habitability as permanence, a comfort zone where existence endures. But the universe teaches otherwise. Even the conditions for life are transient, passing through systems like seasons through a forest. What we call stability is only a moment in motion, and yet perhaps that is where beauty lies. Because life itself is motion, the constant adjustment to change. On planets where warmth drifts and stars evolve, life would learn to follow the heat, to migrate, to adapt, to transform. It would not cling to one temperature or orbit. It would flow with the rhythm of stars like water following gravity. Maybe that is what the universe wants of life, not permanence but participation. To join the cosmic tide of transformation, to flicker brightly, while conditions allow to fade gracefully when they end, and to begin again somewhere else. In the quiet logic of celestial mechanics, the habitable zone is never still. It is a moving promise, a travelling spark, the universe's way of saying life is not a place. It is a pursuit. Every world, every moon, every atom of home began inside a cloud. Not the gentle clouds of a planet's sky, but vast luminous nebulae, interstellar nurseries of gas and dust, where gravity and radiation wage their ancient war. From within these swirling veils of chaos, stars ignite, planets gather, and the architecture of solar systems begins its slow unfolding. These are the nebula cradles where order first learns to emerge from disorder. Seen from afar, a nebula looks serene, a soft bloom of colour across the dark pinks and blues shaped like flowers or wings. But inside the story is anything but calm. The air there, if one could call it air, is a storm measured in light years. Gas flows in shock waves sculpted by nearby stars and supernovae. Ultraviolet radiation burns cavities through dust. Magnetic fields twist, tangle and break. The result is a landscape of chaos, glowing walls, dark filaments and caverns of shadow where matter gathers to hide from the storm. In those shadows, gravity begins its quiet work. A single dense knot, perhaps only one part in a million denser than its surroundings, starts to collapse. As it does, it pulls more material inward, heating as it shrinks until at last a faint glow appears at its center, a protostar wrapped in a cocoon of dust. Around it, a swirling accretion disk forms the first sketch of a solar system. Inside that disk, temperature draws invisible boundaries. Closer to the newborn sun, rock and metal condense. Farther out, ice and gas survive. This simple gradient, born of distance and heat, decides the fates of planets not yet formed, which will be rocky, which gaseous, which icy and remote. The process is slow and unrelenting. Grains collide, stick and grow. Pebbles become boulders, boulders become planetesimals, and within a few million years the chaos finds its rhythm. From turbulence arises geometry, the flatness of planetary orbits, the symmetry of rings, the spiral flow of matter, all born from friction and gravity, from the dissipating roar of the cloud. The same forces that once tore the nebula apart now shape it into harmony. Yet even as new stars are born, old ones die nearby, sending shockwaves that compress new pockets of gas, triggering more collapses. Creation and destruction overlap. A single nebula can hold both infant suns and stellar ghosts, glowing hydrogen from one generation, lighting the birth of the next. The Orion Nebula, only 300 light-years away, glows this way ultraviolet light from young massive stars carving out its walls, while smaller stars gestate in the remaining dust. It is a living laboratory of cosmic inheritance, one generation sculpting another through radiation and gravity. If you could drift within it, you would see motion made visible. Columns of gas a dozen light-years tall, lit from behind by newborn stars. Shadows of cooler dust stretching like fingers into glowing space. Every photon you saw would have travelled through layers of carbon, oxygen and hydrogen, the same ingredients that will one day form waterstone and life. Each wisp of gas is a possibility, each sparkle a sun not yet fully born. The violence of these births is unimaginable. Jets of plasma shoot from the poles of protostars, carving tunnels through the surrounding gas. Shocks heat the nebula to thousands of degrees. The newborn star, still hidden, begins to radiate its first wind, a breeze that will one day clear away the dust, ending its own gestation. When that happens, the cradle evaporates, leaving behind a small, bright star surrounded by a disk of debris, a promise of planets to come. Astronomers call this transition the moment of ignition, when gravity's slow collapse gives way to fusion's steady fire. The star begins to shine not by falling but by burning, and the nebula that birthed it becomes its first victim and its first gift. Philosophically, there is no clearer image of the universe's method: creation through release, order through exhaustion, light born from compression. Every star is the outcome of pressure giving way to peace, every system a testament to the patience of chaos. In that sense, the nebula cradles are not just the beginning of stars, they are the beginning of story. The chemistry we trace in comets, the oxygen we breathe, the carbon that shapes our lives, all were once particles adrift in a glowing cloud, waiting for gravity to gather them. The very dust we see in our telescopes is ancestral. It has burned and cooled and been reborn across generations of stars. If you could touch the light of a nebula, you would feel history the weight of 1,000 suns not yet kindled. And if you waited long enough, you would watch the chaos thin, the clouds fade, and the first stable orbits appear, the quiet signature of order's arrival. When the last of the dust clears, what remains is simple a star, a few circles of matter, and silence. But within that silence, the memory of turbulence still glows, because every sunrise, every planet, every heartbeat of light is in truth the echo of a nebula learning to dream. Most stars live in quiet suburbs scattered through the spiral arms far apart, each with its own dark between. But some are born and live their entire lives in the crowded hearts of the cosmos, where stars huddle by the millions glowing shoulder to shoulder. These are the stellar cities, dense clusters and galactic cores where night never truly falls and the sky is bright with the constant shimmer of suns. Imagine standing on a planet there. Above you, instead of the faint scatter of constellations, the heavens would burn with 1,000 neighbouring stars, each one close enough to cast shadows of its own. The night would never be dark, it would be the colour of perpetual dusk, a soft golden haze where every direction holds a sun. You would never see the Milky Way as a band because you would be inside it, its stars crowding your horizon like towers of light in a cosmic metropolis. Such places exist. Globular clusters, ancient spherical congregations of stars, orbit the Milky Way like luminous satellites, each holding hundreds of thousands of suns within a few dozen light years. In their cores, stars are separated by distances of only a light week or less, close enough for gravity to tug, to disturb, to reshape orbits. Every system there lives under constant negotiation, its stability a fragile truce between its star, its neighbours, and the larger cluster that binds them all. To a planet, this is life in a gravitational crowd. Passing stars can shear orbits, pull comets inward, or strip planets away entirely. A close approach once every few million years might scatter a planetary system, trading worlds between suns. In the densest regions, planets might drift freely, captured and recaptured, cosmopolitan bodies are wandering from star to star, citizens of no single home. And yet not all is chaos. Even in such thronging environments, order survives. Simulations show that stable planetary orbits can persist around stars in cluster outskirts, or even within cores, provided they lie close enough to their host within a few astronomical units to resist external pull. There, life could exist beneath a sky dense with light dawns that glow silver nights pierced by constant radiance. Seasons might be influenced not only by one sun but by the varying brilliance of the stellar city itself, a place where the galaxy's heartbeat is visible. The galactic center amplifies this vision further. Near the heart of the Milky Way, where a supermassive black hole anchors the galaxy, millions of stars orbit within a volume smaller than the space between Earth and the Pleiades. It is a region of fierce radiation and gravitational flux, yet also of astonishing beauty. If a planet could survive there close to its parent star, shielded by magnetic fields, its night would blaze like a chandelier. Dozens of suns would rise and set each hour as it rotated. Shadows would overlap, directions would lose meaning, and darkness would become a rumour from faraway space. The Chandra and Hubble telescopes have shown us glimpses of these places, knots of blue and gold newborn clusters swirling around the galactic core. Some are mere millions of years old, still shedding the gas from which they formed. Others, like the globulars, are relics from the universe's youth, 13 billion years old and still burning quietly together. In both, the theme is the same: proximity as endurance. Stars here do not live alone, they share light, heat and gravity, their lives intertwined like neighbouring cells in a living organism. For life, the challenge would be intensity. Supernovae could ignite nearby with devastating frequency. Radiation storms might sterilize entire regions. Yet such energy also stirs chemistry, seeding nearby clouds with heavy elements enriching new generations of stars. Even destruction in these dense neighborhoods becomes creative. If you could watch from afar, a stellar city would shimmer like a galactic heartbeat, stars orbiting one another in slow motion, their collective gravity breathing in and out. To drift through one would be like flying between skyscrapers of flame through avenues of light where the traffic is made of suns. And perhaps that is the paradox of the cosmic city, that in its apparent chaos lies the deepest order. Each star follows its own orbit, precisely obeying the same equations as those that govern the calm of distant solitary systems. What feels like confusion is on a cosmic scale, a symphony of precision, billions of bodies bound by gravity's silent choreography. The night sky from such a world would teach a lesson our own dark heavens cannot, that light is not rare but common, that solitude is not the universe's default, and that even in the densest chaos stability can persist if harmony is shared. For perhaps that is what the cosmos tells us from clusters to galaxies, that survival is not isolation, it is coexistence. The stars of these crowded neighborhoods endure because they move together, because each balances the other's pull. In their collective brilliance, we glimpse the pattern of all creation, a city of stars radiant and restless, where even amid collision and gravity's noise, the universe finds room for order to shine. The universe has no border guards. Planets are not always loyal to the stars that bore them, and suns are not always faithful to their worlds. Across billions of years, the galaxy has staged a quiet drama of exchange and theft, where gravity, not allegiance, decides who belongs to whom. In the open expanses between stars, every close approach is a negotiation. When two stellar systems drift near each other, passing within a few light years, their outer planets and comets feel the pull of both. A slow, invisible tug-of-war begins. Sometimes the visitor wins. A planet's orbit stretches, fractures, and finally snaps. When the dust settles, the world now circles a new sun, its sky forever changed, a captured immigrant in another star's domain. Astronomers call this process gravitational exchange or stellar capture, and it is more common than we once thought. The Milky Way is not static. Stars wander, spiral arms, churn, clusters, dissolve. Over billions of years, such encounters accumulate, turning planetary systems into cosmic marketplaces where worlds are traded, lost and found again. The outer reaches of our own solar system may already carry evidence of this. Objects like Sedna and Lelecahonoa trace elongated orbits far beyond Neptune, too distant and too tilted to have formed here. Some scientists suspect they are adopted, drawn in long ago when the sun passed close to another young star, captured not by choice but by chance. At the galactic level, these trades are quiet but constant. In the dense birth clusters where most stars form, the odds of planetary theft can reach 10 to 20%. Young suns pass within 1,000 astronomical units of each other, close enough that gravity brushes against gravity, reshuffling outer planets like cards on a table. A single flyby can eject one world into space and pull another into orbit. In this way, planets become interstellar orphans, drifting between systems until they find a new gravitational home. Some never do. These are the rogue planets, the wanderers adrift in darkness, bound to no star. They roam the galactic plane in numbers that may rival all bound planets, combined tens of billions of lonely worlds, moving in silence, carrying the signatures of the stars that once held them. Each is a lost story, a page torn from a cosmic book. And sometimes one of those pages drifts close enough to be read. In 2017, telescopes caught sight of a strange, slender object streaking through our solar system, Oumuamua, the first confirmed interstellar visitor ever observed. It came from no known trajectory, moving too fast to be bound by the sun, tumbling end over end as if shaped by another sky. At first, astronomers thought it a comet. Then they realized it had no tail, no outgassing. It was something new, a fragment from another system passing through ours by sheer coincidence. Since then, surveys have revealed that such objects are likely common. New research from 2024-2025 suggests there could be trillions of interstellar fragments, cometary shards, frozen planetesimals, even full rogue planets wandering the galaxy. These relics may be seeds of exchange, the raw material by which planetary systems share chemistry across light years. They carry isotopic fingerprints from distant suns, silicate dust from alien protoplanetary disks, carbon chains that hint at organic potential. When they pass through another system like Oumuamua did through ours, they briefly bridge stellar histories, turning isolation into continuity. Some of these travelers may even settle down, if their trajectories slow as they pass near a star, radiation pressure and gravitational drag can capture them permanently. Simulations show that over its lifetime our Sun could have quietly collected dozens of such visitors, now frozen in deep dark orbits near the Oort cloud, adopted citizens from forgotten worlds. The process is not theft in the human sense. It is more like exchange without consent, the universe's form of drift and inheritance. Gravity does not care where a world began, it only cares where balance can be found. A captured planet soon forgets its original sun. Its climate adjusts, its chemistry evolves. Its skies repaint themselves in new constellations. In time it belongs as fully as any native world. And what of those that wander forever, never captured, never destroyed? They continue the great circulation of matter, the galaxy's slow respiration. Each rogue planet is a vessel of continuity carrying metals forged in one star to perhaps seed another. Each Oumuamua-like traveller is a letter in a cosmic language crossing the interstellar dark to remind us that systems are not isolated. They are porous, connected, exchanging not only material but memory. From a philosophical view, it is humbling. We think of solar systems as self-contained families, tidy and permanent, but the truth is fluid stars steal, share and lose their worlds all the time. Creation does not happen once it keeps redistributing itself, scattering possibility like pollen through the galaxy. So perhaps somewhere out there a planet now circles a red dwarf it never knew, in its youth its surface frozen, its sky strange, its ancient core still whispering of a sun long gone. And perhaps one day something from that world, a rock, an atom, a thought, will wander again and find us. Because in the cosmic marketplace of gravity, ownership is temporary, everything drifts, everything is shared, and every world in the end belongs to the galaxy itself. In the universe, nothing is ever truly lost. Stars die, but their remains do not vanish. They become soil for the next generation of worlds. Ashes turn to dust, dust gathers into disks, and from those disks rise planets, once again. This is the recycling of creation, the cosmos practicing its own quiet form of reincarnation. When a sun like ours reaches old age, it sheds its outer layers into space, forming a glowing shroud of gas, a planetary nebula. At its center remains a white-hot ember, a white dwarf smaller than Earth, yet heavier than the sun, shining with residual heat. Around it, the expelled material continues to orbit, drifting in complex eddies of gas and dust. And within those remnants, under the steady pull of gravity, new structures begin to take shape. Astronomers once assumed that planetary death was final, that the violence of a star's dying breath would obliterate everything nearby. But observations over the past decade have changed that story. Telescopes have detected disks of dust and debris circling white dwarfs, faint rings built from shattered asteroids surviving planets and stellar remains. Some even show signs of ongoing formation, with dense clumps coalescing once more into larger bodies. In 2024, a white dwarf designated WD 1054-26 drew particular attention. Regular dips in its light revealed something remarkable, a chain of orbiting fragments evenly spaced, as if caught in the process of becoming moons or planetesimals. Around a corpse of a star, a new system was assembling life after death in its purest, most literal sense. The physics is simple, but profound. When a star dies, it releases heavy elements, carbon, oxygen, silicon, iron, forged in its heart through fusion. Those elements drift outward, cool, and eventually condense into new dust. That dust becomes the raw material for the next generation of stars and planets. Every mountain, every ocean, every cell on Earth carries the ashes of such a death. We are not made from sunlight. We are made from starlight's residue. Even greater cycles occur when massive stars explode. A supernova tears a star apart in an instant, scattering its elements across light years. The shock waves compress nearby clouds, triggering new star formation. In that same chaos, debris gathers into disks around newborn suns. The calcium in our bones, the gold in our veins, the iron in our blood, all were born in such detonations. Supernovae do not end creation. They propel it. Each explosion is both a death cry and a birth song echoing through the galaxy's spiral arms. From these ashes can emerge second-generation worlds, planets born in the ruins of earlier systems. Some orbit pulsars or white dwarfs, others form inside the enriched gas of supernova remnants. Their chemistry is richer, their materials heavier, their cores more complex. They inherit the memory of their ancestors, the metals of the dead becoming the architecture of the living. If we could visit such a world, we might find a landscape both ancient and newborn. Its rocks would contain isotopes forged in multiple stellar generations. Its atmosphere might shimmer with elements that once belonged to different suns. It would be a mosaic of time, a single planet embodying the history of the galaxy. Philosophically, this process carries the oldest truth of nature. Destruction and creation are not opposites, but phases of the same breath. The cosmos does not mourn its losses, it transforms them. Every end feeds a beginning. A star's death is an act of generosity, the release of all that it made, given freely back to the void to be remade again. The white dwarfs that now cool in silence were once like our sun, and their quiet, glowing embers are surrounded by debris that will one day coalesce into new planets. Those planets may in time host new chemistry, new atmospheres, perhaps even new life. If intelligence ever rises there, it will gaze into its pale sun and see not a god but a memory, a reminder that existence is inheritance, not invention. Even the atoms composing us have been through this cycle before, perhaps more than once. We are not living in the aftermath of creation. We are the continuation of it. Each breath we take recycles the breath of dead stars. Each thought we think is powered by the heat of fusion long extinguished. So when we speak of cosmic reincarnation, we are not speaking metaphorically. We are describing the natural order of things. The universe dies into itself again and again, each collapse giving rise to new fire. Around white dwarfs, in nebula ruins, and inside supernova clouds, the work continues quietly, patiently, eternally. Worlds are built from wreckage, galaxies weave their own afterlives. In the end, the cosmos is not a story of beginnings and endings, but of perpetual becoming. Every ash will be a seed, every ruin a cradle, and somewhere right now in the glowing dust of a dead star, a new world is gathering its orbit, already forming its surface, not yet cooled, its future inhabitants still unwritten proof that in the great cycle of existence, creation never truly stops breathing. Across the galaxy and beyond, the cosmos has written a library of worlds, molten, frozen, gaseous, metallic, worlds that burn, worlds that drift in darkness, worlds that shimmer like mirrors or sleep beneath miles of ice. Each is an experiment, a variation on one theme matter, learning how to arrange itself under gravity's patience. For all their difference, these planets share a single law, the universe's endless improvisation. Given the same ingredients, hydrogen, oxygen, carbon, iron, nature composes symphonies of contrast. It can turn water into steamstone or glass depending on temperature and distance. It can forge iron into rain, diamond into mountains, and silence into light. Each world is a verse in that cosmic song, a stanza where physics and chance rhyme in ways never repeated twice. We have now glimpsed hundreds of such heavens, each stranger than the last. Molten exoplanets glowing like embers, their rocks evaporating into vapor. Frozen giants where air itself has turned to frost. Planets wrapped in magnetic fields so strong they crackle with aurora the size of continents. Mirror-bright worlds reflecting 90% of their starlight. Superpuffs so airy they could float in water, and super Jupiters so dense they nearly ignite. Diamond worlds, ocean worlds, iron worlds, shadow worlds, every form of balance and imbalance that nature could imagine already waiting in the dark. There is no preferred design, only variation. No two systems share the same geometry or composition. Each is a local truth sculpted by its star, its collisions, its history. In that diversity lies the deepest kind of order, not repetition, but continuity through difference. Every deviation from the ideal teaches us that there is no ideal, only what works long enough to persist. To study them is to confront the humility of scale. Earth, once thought unique, is now one note in an orchestra too vast to catalogue. Its oceans are not rare, its skies not exceptional, and yet that realization does not diminish us, it expands us. For the more we discover, the more we see that we are part of an immense improvisation, one that began long before us, and will continue long after. The molten worlds show us what heat can do when it has no rest. The icy ones show us how endurance thrives in silence. The gaseous giants teach us that form can exist without surface. The magnetic and metallic remind us that even invisible forces can sculpt beauty. Each world is a facet of possibility, and together they prove that variety is the universe's signature. When astronomers point their telescopes into the dark, they are not just mapping planets. They are listening to the grammar of creation. Every new discovery, a tilted orbit, a stolen moon, a rogue drifting between stars adds another sentence to that story. And through it all, the pattern is clear: the universe does not seek perfection, it seeks expression. In that recognition, curiosity becomes a kind of reverence. We search the heavens not to find our likeness, but to witness what else is possible, to see how far imagination can stretch when written in gas and dust instead of ink and thought. Each new world is both a question and an answer, a reminder that nature invents without pause, that existence itself is creative. And perhaps in this variety there is a quiet moral. That difference is not accident but design. That harmony is not uniformity but diversity held in balance. That the same laws that shaped stars and storms also shaped us minds, capable of wonder, hearts capable of awe. So when we gaze into the night sky and imagine other worlds, we are not looking outward only, we are looking backward and inward, into the mirror of what creation can do when given time. We are the universe becoming aware of its own artistry, marvelling at the range of its brush. All the molten, icy and ethereal worlds we've glimpsed are not separate heavens. They are variations of one great whole, the cosmic improvisation still unfolding. And to witness it is to understand that humility and wonder are the same thing, the recognition that we are both audience and instrument in a performance still being composed. The heavens are many, the laws are one, and in their unending variety the universe plays its oldest melody, a hymn to possibility sung through light, matter and time. Somewhere above the roofs of cities and the stillness of oceans, the sky turns slow, patient, unending. The same stars we spoke of tonight still move in silence, tracing their quiet geometry across the dark. Planets glide through invisible ellipses, dust drifts through beams of starlight, and time as always keeps its gentle rhythm. You can close your eyes now, nothing will be lost. The universe continues without effort, a clock that never needs winding, a song that sings itself. Every particle still obeys its ancient dance, hydrogen, whispering to gravity photons, weaving through emptiness, each motion both small and infinite. All the worlds we visited, molten and frozen, brilliant and dim, remain where they are, circling their suns in perfect patience. They do not hurry, they do not compete. They simply turn, kept aloft by the same quiet balance that holds your heartbeat steady. Listen for it, the faint hum beneath everything that is gravity's lullaby, the music of existence at rest. It is older than language, older than thought. It is the soft pull that keeps galaxies together, and you upon the earth, reminding both that they belong. As you breathe, imagine the light still travelling from the birth clouds of Orion, from the silver halos of distant worlds, from suns that lived and died before the earth was dust. That light is still on its way, still crossing the dark, still bringing messages from everything that ever was. And here for this brief moment you are listening. You are part of the same story, made from the same atoms that once burned in stars, cooled into dust, and found their way into oceans, air and thought. The universe is not outside you. It is within you, continuing its work quietly behind every breath. So let it turn. Let the galaxies keep their watch. Let gravity keep time while you rest. Somewhere a newborn star begins to glow in its nebula cradle. Somewhere a comet writes a brief line across the dark. Somewhere a planet far from any sun still drifts unafraid of the cold. And here, in this small corner of everything, you can rest, too held by the same laws that hold the cosmos. Tonight the universe does not ask for thought or wonder. It asks only for stillness, to remember that even silence has motion, and that sleep like gravity is a gentle return. So breathe once more. The stars are still where you left them. The light still travels, and the universe, vast, calm, eternal, is already whispering its answer. Good night, traveller. Sleep easy beneath the turning of the heavens, for the cosmos keeps watch, and its song, soft and endless, is still being sung. Thank you so much for keeping me company tonight. Don't forget to subscribe so we can share many more stories together.